Yeah. So good morning, everyone. Great welcome to all of you. And thanks for coming here. And we are really pleased to have this conference. I mean, in math science, after a long period, due to pandemic, we are starting to have our regular scientific meetings and so on. And as you can see there, we are also celebrating 60 years of math science. So it's a great occasion to have all of you here, and thank you all for coming. And we have, so we are, as you know, we are, the focus of the conference is non-equilibrium physics, and we have a great range of talks on this theme that you will listen to in the next 3-4 days. So without much ado, let's start. I'll request Professor Ravindran, our director, to say a few words of welcome.
Good morning. Warm welcome to all of you to our institute. As Pinaki said, actually we are celebrating 60 years of completion of 60 years of our institute, and I think when we enter into the 61th year, this is the first meeting. So I'm really happy to have a meeting quickly after this celebration. So it will be remembered forever, actually, I suppose. Not only for this, but also for the physics content that you're going to discuss in this next 4 days. As you all know, that IMSC is an institute where 4 different kinds of things, science are done, actually. Theoretical physics, computer science, theoretical computer science, mathematics, and computational biology. And we not only work independently, we also actually interact with each other. It's an unique institute in India where 4 different things are done in a single place, and every one of us doing on things that do not overlap too much with others. So it's like a 50 different disciplinary that is being done. So it's an unique institute. You can also actually outside this auditorium, you can also have corridors where you can see people working, and if you are interested, you can also have a chat with them actually when you get time. I'm sure you will be busy next 4 days. Won't have too much time for these things. But of course, I just wanted to say that we have quite a lot of things done here. And of course, you'll enjoy the weather. This is the nicest part of, nicest duration of Chennai, actually. I won't take too much time. You have a lot of things to do for the next 4 days. Again, welcome to all of you, and enjoy these 4 days of Tamil Nadu cuisine and Tamil Nadu, weather, everything. Welcome. Yeah.
Thanks, Professor Ravindran. So we'll start our scientific proceedings. The chair for the first session is Professor Pavan Kumar. Yeah, Pavan, over to you.
Yeah, so good morning, everybody. So we have 4 talks lined up in this particular session, and the 2 talks will be in the first half of the session, followed by a tea break, and then the 2 other talks. So without taking much time, I welcome Professor Abhishek Dhar from ICTS TFR Bangalore to talk about entropy growth during free expansion in specific ideal gases. Abhishek.
You can just leave it.
So yeah, the talk is for 40 minutes, with 35 minutes heads up, and there'll be 5 minutes break for discussions. So.
Okay, so first I would like to thank Pinaki and Arnab for organizing this and for the invitation. Okay, so yeah, it's really nice to be in IMSC after a long time. I mean, I don't know when I was last here. I think maybe around almost 10 years back, maybe. Okay, so yeah, so I'll be talking about entropy growth during free expansion of an ideal gas. So this work is done with a large number of people, and it's still going on. It's various things. So Shubhadeep Chakravarti, who was an I think he was at IMSC at some point, but he was a postdoc at ICTS and now he's in Nuremberg. Two of my students, Junaid Bhatt and Saurav Pandey, two colleagues at ICTS, Manas Kulkarni and Anupam Kundu, and Shelley Goldstein and Joel Lebowitz at Rutgers, and David Hughes at Princeton. Okay, so some of this is published in these papers and some of it is still being written up. So, okay, so the basic question is something everyone has thought about. I mean, we have the microscopic laws of physics are reversible, but why do we see irreversibility in nature, right? So this is the simple demonstration of that. You take a glass of water and then you put a drop of ink somewhere, and then what you observe is, of course, after some time you see this, you see eventually it becomes a homogeneous mixture, and you never see things going the other way around, right? Even though the microscopic laws say that this is of course possible, that it should go from here to here. Okay, so this is something we all have thought about, and in some sense we probably have some understanding. Okay, so the observed macroscopic behavior of physical systems show irreversible behavior. So we know that the second law in some sense provides an arrow of time and quantifies irreversibility through the concept of an entropy function which always increases with time. Okay, so note that entropy is usually defined for an equilibrium system, and what we say when we say entropy increases, it's like you have some system and you release some constraint. So initially it was in equilibrium, and after you release the constraint it goes to a new equilibrium, and from one equilibrium to the other equilibrium the entropy you can calculate, and the entropy has what you expect is that the entropy should increase. Okay. So okay, so this is of course the question that everyone asks. I mean, how do you get irreversibility from reversible microscopic dynamics, which can be either Newton's equations or Schrodinger's equation. Okay, so okay, so this is something which Boltzmann had thought about a long time back, more than 100 years back, and what he observed is that this irreversibility is the most important idea is that that you need a large number of degrees of freedom. Okay, so what he said is that the observed irreversibility is the typical macroscopic behavior given appropriate initial conditions that becomes a certainty when the degrees of freedom is large. So I mean, it depends on initial conditions. You start with very initial conditions typically, and then this irreversibility that we observe is the typical behavior. Okay, so there is also atypical behavior is possible, but that becomes rare when the degrees of freedom are large. Okay, so Boltzmann in fact provided a very clear prescription of how one can construct an entropy function for this irreversible dynamic. Okay, and this entropy is defined for a pure microstate. Okay, so this is actually the main idea that I will try to present in the talk, that you can define an entropy function which is defined for a single microstate of a dynamical system. And this entropy function can be defined both in or out of equilibrium, and in equilibrium it is equal to the usual entropy we know, but it can also be defined out of equilibrium. Okay. So this is the main idea, and this has been discussed in a lot in the literature. Some sort of references that I like are, this is a very popular article, Physics Today, by Joel Lebowitz. It's called Boltzmann's Entropy and Time's Arrow. This is a more technical paper which has a lot of the details of the formalism which I'll discuss today. This is something which is an extension of this earlier work to the quantum case. I mean, all these other papers. Okay. So in this work that I will present today, basically it's an sort of very explicit, simple pedagogical example to illustrate this Boltzmann's ideas of constructing this entropy function. Okay, so that's the basic idea. So please ask questions at any point. Okay, so this is what the system will look at. It's ideal gas in one dimension. So let's say I have a box which goes from 0 to L, and there are n particles. These are point particles, so I have drawn them as disks. These are really point particles which are completely non-interacting. Okay, so they can go through each other, and the dynamics is just ballistic dynamics. So each particle moves with some constant velocity, and at the ends it can reflect. Okay, but otherwise they just go through each other and they're moving with constant velocity. That's the dynamics. Okay, and the initial condition what we take is that half of this is, let's say, just half of the box is filled with particles, and each particle has a velocity which is chosen from a Maxwell distribution. Okay, so it's in thermal equilibrium, but on one half of the box, and then what we do is we remove this wall, and so that's the free expansion setup, right? That's what we usually study in free expansion. Okay, so this is the initial condition. It's in a thermal distribution, but we choose one realization. Okay, so we don't do an average over realization, which also one can do. We just choose one realization from the equilibrium distribution. Okay, and the particles, this I already said. And okay, so now if I ask what do you expect, even though it's a non-interacting system, there's no chaos or anything, what you naively expect is that at long times this system would in some sense equilibrate. At least if you look at the density profile, it reaches a uniform, and that's what you expect, right? It should go to a uniform state. And some things may not relax, like the velocity distribution, because it's non-interacting, it wouldn't change with time. But it started with Maxwell, so it will stay Maxwell for all times. Okay, so in some sense we expect that it's going to from some macroscopic state, which is this half-filled box, to a uniformly filled box. So there is some irreversibility we expect, and how do we quantify this irreversibility? Okay, so the basic idea of Boltzmann is the following. So there are two descriptions of a system. One is a microscopic and one is a macroscopic description. So the microstate of this system I am talking about, it's n particles, and is described by positions and momenta of all the particles. So this is the microstate, which I'll label by capital X, right? All the positions and momenta. And then the dynamics is given by some Hamiltonian. And then one can talk of macrostate, which is a coarse-grained description of the system. Okay, so now when we observe a system, like say in the gas in the room, we don't observe all the molecules. We might be observing something like maybe what's the number of molecules in even like small boxes in this room, right? That's what we can observe. So it's a coarse-grained description. This is what we are able to observe. Okay, so such a description describes a macrostate. Okay, so this is an example. I mean, if I have this box, particles in this box, then if I just ask what is the number of particles in the left half, that's a macro variable. Okay, so this n left is the number of particles in this left half, and that of course is a function of the microstate, right? So this it's a some function of the microstate x. Given the position and momentum of all the particles, I can immediately compute what is the number of particles on the left half. So it's a function of the microstate. Okay, now the idea of Boltzmann is that if I just specify the macrostate, which is the number of particles on the left half, then I know immediately that there are a large number of microstates which will give me the same value for the macrostate, right? So we just say, let's say gamma m be the number of such microstates, or the volume in 6n dimensional phase space, which corresponds to the same value of the macrostate. Okay, then Boltzmann's entropy for this microstate x is just defined as log of this total number of accessible microstates. Okay, so notice that this looks very similar to what we do in equilibrium physics, right? What is the entropy of system described by energy E? We just compute the volume in phase space, which is for which the energy is between E to E plus delta E, and then take log of that, right? But here what we are doing is that we ask that what is the value of the macrostate And then we ask what is the volume in phase space, which has the same macro state. Okay, and that gives us the entropy. Okay, so what's good is that we can compute entropy for a single microstate. Okay, so just to give an example, I mean, this is, let's say we take a box like this and we partition it into several cells. So this total length is 7, and I divide into 2, 1, 2, 3, 4, 5, 6, 7 cells. Each cell is size 1. And let's say I just put 16 particles, right? So a microstate would be the positions of all the particles. And this is the macrostate where I count the number of particles in each cell. So given a macrostate, of course, I can have large number of configurations, and I can ask how many such microstates are there for a given distribution of particle numbers. Okay, so in this case, if I know the number of particles in each of these cells, then I can count how many different possible arrangements are there which give me the same number, and this we know that it's given by some formula like this. So delta is just the size of each cell. So delta to the power Na is the number of particles in this cell divided by Na factorial, right? This is the usual volume, sort of volume in phase space for a given, yeah.
Is there macrostate n? It's not unique, right?
Yeah, the choice of macrostate depends on what we are observing, right? I mean, like you can observe various things. Like in this case, I can choose to observe just the number of particles in each box. I can also choose to observe the number of particles and their momenta in each box. So that's up to what I am observing.
So the Boltzmann entropy would be different?
Would be different, right? Yeah.
And
yeah, right, yeah.
So is Boltzmann entropy and thermodynamic entropy two different?
Right, yeah. So for some choice of macro states, what we'll see is that if the system is in equilibrium, then I mean it agrees with the equilibrium definition, right? I mean, so yeah. So this, I mean, if I just look at n, of course, it won't give me the equilibrium distribution, but because I'm ignoring momentum variables. But if I mean, if my, like, I may not be able to look at momentum, right? So if I'm just observing like positions, then this is a good description. Okay, so. Okay, so this is the usual counting of number of states corresponding to a given configuration of number of particles. And then if I compute the entropy using this Boltzmann's prescription, then I get some formula like this. So finally it's rho A log rho A. So this is the density of particles in a cell, in the 8th cell, and times log rho A, and I just sum over all the cells. Okay, so this is rho log x dx. I mean, this is the kind of formula that you will remember is the entropy associated with a particular density profile of any microscopic system. Okay, so now, so then the basic idea of irreversibility is the following, that let's say this is the entire phase space. Now this entire phase space, like for a given macrostate, value of the macrostate will correspond to some volume in this phase space, right? That's what I just, and taking the log of that gives me the entropy. So now the entire phase space can be partitioned into parts, each of which correspond to some value of the macrostate. Okay, and the equilibrium macrostate is one which has actually extremely large volume. It occupies almost the entire phase space. Okay, so in a typical non-equilibrium setup, what happens is that one starts from some from extremely low volume region of phase space. So low volume means if I look at the number of configurations, microscopic configurations for all the particles in this room being in 1/2, right? That's a very unlikely configuration. So it will occupy a very small volume in this entire phase space. Okay, so my initial condition will belong to some very small part of this phase space, and then it's evolving. As it evolves, it's basically going to volumes of larger it's going to cells which have larger volume in this phase space. Okay, and eventually it goes to the equilibrium cell which has the largest volume. Okay, so that's the rough idea of why we observe irreversibility. Okay, so again, just to summarize, like how one can associate an entropy for an individual microstate, just or an individual wave function for quantum systems. So this is the microstate, and what we say is that we our observables are coarse-grained variables, and they are, of course, given this microstate, we can find what is the value of this coarse-grained variable, right? So given the microstate, we can immediately say what is the number of particles in each cell, which is our macro observable. Then what we do is just count the number of microstates corresponding to this value of the macrostate, and so this is this gamma, and then take log of that. That gives us the entropy of the microstate. Okay, so what's most important to observe is that we have entropy for a single microstate as opposed to an ensemble, which is what we usually we are used to. Okay, so now like Jitendra asked, I mean, there are many choices possible for the macrostate. So we'll discuss two sort of very natural choices of macrostates in the context of an ideal gas. Okay, so the two macro variables that I'll discuss are, so one is just the empirical single particle distribution, which is this object. So basically you just ask, I have an n particle system with 2n degrees of freedom, but I just ask, like, in a how many particles are there which are located in some cell around xv in single particle space. Okay. Okay, so this is, of course, one is familiar with this. This is what arises in, for example, Boltzmann's H theorem and so on. And the other set of macro variables that we'll look at are the usual hydrodynamic fields that are described that are used to describe a fluid, for example. Okay, so for example, the air in this room, the usual description in fluid dynamics is in terms of the density, the momentum field, and the energy field, right? So, so we just take small cells in this room and ask what is the total number of particles in this, what is the total number of, what is the total amount of momentum, and what is the total energy in this cell, and we do it for all the cells in this room, and that is our coarse-grained description. Okay, it's clear that this is a coarse-grained description because there will be a large number of microscopic states which give me the same values for these fields. Okay, so these are the two coarse-grained descriptions of our microscopic system that we will discuss. Okay, so let me first discuss the first, this first choice, the single particle empirical distribution. Okay, so again, what we do is we have a single particle phase space where this is position and velocity, and we divide it into grids, into small cells with delta x in this direction and delta v in this direction. And we, so given a microstate, we can just ask each particle will have a position and velocity that will be a point in this grid, right? So we put all the, so we just see where all the particles lie in this phase space, and then we just count how many particles are there in each grid. Okay, so let's say n alpha is the number of particles in the alphath cell, and we then compute this function f alpha, which is just the fraction of particles in each cell. And then from the then we just do this counting. We ask how many realizations are there which have the same number of particles, and this using the same argument that I just gave to get this rho log rho. In this case, we'll get an entropy which looks like this. Okay, so given a microstate, I can immediately find what are these values of F alpha for, the distribution of number of particles in each of these cells, and then I can compute the entropy. Okay, so note that this is for a single realization. I'm not doing any ensemble average or anything. Okay, so this is the entropy, and we want to know in this as the system evolves from this in this free expansion scenario. Yeah.
Why is this single particle phase space? Because there I can see like multiple particles in the phase space.
No, so there are n particles which are x1, p1, x2, p2, and so on, x1, xn, pn. But I'm looking at just the single particle phase space distribution, right? Which means in this two-dimensional space, I'm asking how many particles are there. See, if I take any particle, it will fall in some point here, right? Then I just count the number of particles. So, I mean, this is not, the n particle phase space would be 2n dimensional, right? But this is just 2-dimensional. So, in that sense, it's a single particle phase space. But each particle, every particle will be some point in this space. Okay, any other questions? Okay, so right, yeah. So it's clear that for as this gas evolves, I can compute this function at any instant of time, just following one individual trajectory. Okay, so this is again just to remind you what is the initial condition. This is the initial condition. Each particle is chosen from a Maxwell distribution, and they are uniformly distributed in this left half. Okay. Okay, so now if I, so this is the single particle phase space. So initially this is how all the, if I just point, put the coordinate of each particle at some point in this space, and this is like I think maybe 10 to the power 5 or 6 particles chosen from that distribution. Okay, so they all lie on different points, and then I just see how these points evolve in this two-dimensional phase space. Okay, so after some time, what we'll see in this, if you just do this new simulation, you'll see that it develops this kind of structure in this phase space. So it develops these stripes in this direction, and so in space it's kind of uniform, but in the velocity direction you can see that it develops this stripe structure. Yeah.
Velocity distribution, which is initially chosen Maxwell.
Yeah. It will stay Maxwell, right? Because these are non-interacting particles. So when particles, they just go through each other. So there's no.
Suppose one particle has velocity 4.
Yeah. It will remain 4 all the time. Right, yeah. So, but it's, yeah, so they are of course distributed from a Maxwell distribution, but each particle maintains its velocity. So we'll also discuss the interacting case where of course they exchange velocities and it's different, but in this case there's no change in the velocity distribution.
Is velocity just coming due to confinement or that's like, these structures are developing just due to the boundaries, or I don't know.
No, so okay, so here I'm showing hard walls. I mean, even if you do it on a ring, you will see the same structure. So basically what happens is, what you can imagine what happens, right? These particles out here, they'll start moving, they are all positive velocity, so they start moving in this direction, these guys move in this direction, right? So this kind of stretches, okay, and then it winds around. Okay, so you just get different windings, and there's no spreading because it's a non-interacting system. Okay, if it is an interacting system, then we'll see later that this will become completely homogeneous. So the fact that this structure is maintained is just because it's non-interacting. Okay, so now given this like distribution of points, we just form our grid, count the number of particles in each cell, and then compute this object. And what we'll do it is we'll use different grid size, this cell sizes. Okay, and see how this entropy growth depends on this cell size. Okay, so what we would like is that this eventually there should be some thermodynamic limit where you take large number of particles and grid size going to 0, and the entropy, this growth function doesn't change with time. Okay, so this is the plot of the entropy growth for different grid sizes. So delta x we keep fixed, while delta v we keep changing, making it smaller. Okay, so it turns out in this model, as you can see, if you delta x is the cell, the grid size in this direction, it's kind of homogeneous in this direction, so you don't expect anything to change when you change delta x. Okay, but if you change the grid size delta v, at some point it will start seeing the structure, right? So you expect that things will depend on delta v, because entropy is basically like it has information on the structure. So question is how much structure can we see in the distribution. Okay, so this is what we see. So this is for some grid size, and then the entropy starts from at time 0 at some value, which corresponds to the half-filled box, and then it increases, and then there are some small oscillations, and it saturates to some value. Okay, so this is for grid size 0.5. This is for a smaller grid size 0.25, and this is 0.1 and 0.05. Okay, so in all cases we see that the entropy eventually it will go to a saturation value, and this change in entropy is exactly log 2, which is what we expect for this free expansion from half volume to full volume. So this change is always log 2, but it just takes longer time if you have a finer grid. Okay. Okay, yeah. So this realization is for 10 to the power 7 particles, and okay, so in this plot, you can see there are two plots. So the one is the blue thing, and one is the squares. The squares are with just a single realization, and the lines are when you also do some averaging over initial conditions. Okay, so you can do average over initial conditions with, always the same macroscopic state. And you see that a single realization and average agree perfectly. Okay, so now you can look, so instead of looking at the entropy, you can also look at this, the actual distribution function, how it evolves in time. And what you see is that at time 0, okay, so this is space and this is momentum and this is f of xv. So at time 0, okay, this is a box of size 4 and the particles are between 0 to 2, so you have only distribution this side, and here there's nothing, right? And after some time what you see is that there's the gas fills the box, so you get a velocity distribution every time, and it's not okay, so now you see that it's no longer Maxwellian if you look at each cell. Okay, because locally, you can imagine at right in the beginning there's nothing in the right half, but the fastest particles will move into the right half, so it will have a velocity distribution which is not really Maxwellian, right? Okay, so this is at time 8, but at time 16 what you see is that it's almost now Maxwellian, and then again at some time you see there's some structure develops and so on. Okay, and so you see this funny sort of periodicity in the distribution with time, which sort of corresponds to what these oscillations that we see. Okay, how much time? I took 25 minutes.
I have about 12 minutes.
12, okay, thanks. Okay, so okay, so I just want to say that this time here 16 corresponds to this peak here, and then this time 32 corresponds to the second peak in this entropy curve, and this times in between are the ones where you have a dip in the entropy. Okay, so you have a dip in the entropy because there's some structure is developing, while at at this other times it's in some sense more homogeneous. Okay, so this we can understand why this is happening. So basically the period of this oscillation is given by 2L divided by the grid size delta V. Okay, so basically it's like if you have a circle of size 2L, then if you have two particles which are starting with velocity which is delta V different, then you ask how long will it take for them to catch up with each other. Okay, so that time is 2L by delta V, and that corresponds to the time it takes for this winding that we saw in this phase diagram to actually for one winding. Okay, so that's why every time there's a full winding in phase space, I mean in some system, in some sense the system becomes homogeneous, and so you see the peaks in the entropy. Okay, so this is how we can understand these oscillations. And okay, so let me just summarize the main observations for this macro state 1. For any coarse graining, so coarse graining means choosing delta x and delta v. The final change in entropy is always log 2, but as the coarse graining box size is decreased, when we decrease delta v, we see that the entropy growth rate is decreased, and it takes a longer time to reach the saturation value. Okay, this function in the large n limit and in the delta v going to limit, one can show that this function actually satisfies this simple Boltzmann equation with no collision terms, and therefore it makes sense that in this limit there's no increase in entropy. Okay, but so if you really take the thermodynamic limit n infinity and delta v going to 0, then there's no entropy production. But for any in this non-interacting system, but if you really have any finite coarse graining, then you always see entropy production. Okay, and this, like I said, for different delta v, you get these different curves, which you can actually scale them by using the periodicity. So they all fall on top of each other, and we can compute these curves and so on, which is I won't describe how one can obtain this. Okay, so these are given in the paper, so I won't discuss this scaling function and so on, which we can completely compute analytically. Okay, any questions? Yeah.
The grid sizes
So the grid sizes of dividing the total box, does that affect the oscillatory behavior at all, or?
Yeah, the grid size, that's what I said. So okay, so when you change grid size, like in this case change delta V,
right,
what you see is that, okay, so see the saturation comes later, and
but it still saturates to the same value.
It will always saturate to the same value,
right,
only the time scale
only
changes.
the time scale is
right,
coming
yeah,
different.
Yeah, so the time scale is this 2L by delta V, right? So delta V smaller, it's a
right,
longer time scale. The period changes and the
right
time scale.
And so in a given grid size,
yeah,
now you have this different deviations from Maxwell distribution, right? So while this deviation is happening, the particles are then undergoing different kinds of displacements per unit time. Is that a physical way to understand it, or like during the time evolution,
yeah,
the particles are undergoing different levels of displacement in a given unit time, like different mean free paths throughout the motion? Is that one way to understand it?
No, see, there's no mean free path. Mean free path is infinite, right? Because they're not completely non-interacting.
Right,
So
but in a displacement point of view, like throughout its motion, like in given unit intervals of time.
See, right, I mean, in the beginning you can see that, see what happens in the beginning here. So you are asking about this plot, right?
Yes, based on this plot.
Yeah.
In a given unit interval of time,
yeah,
say 1 unit of time or 2 units of time, at the beginning it covers some separation,
yeah,
from one point to point B, and then in an intermediate state, in the same unit of time difference, it covers a significantly different distance, or is that completely uncorrelated?
Okay, I'm not sure I understand. Maybe we can discuss later,
sure,
right?
Sure.
Okay, so now I'll discuss the second macro state that that I mentioned, where you just divide this this box into cells of size L, and then you just ask what is the number of particles in this cell, what is the total momentum and energy for different cells which are centered around this point, different positions X. So this is the usual hydrodynamic description of fluid. So we can then define this density, energy density, momentum density fields. And in this case, if you ask, again do this counting, what you'll find is that the entropy is just given by the size of the cell into the usual thermodynamic entropy in each cell. Okay, so for each cell, since you know the number of particles, their momentum and energy, we know from usual thermodynamics how to compute the number of microstates, right? So we don't care whether the system is in equilibrium or not. This is just a counting strategy. Okay, so to count you can use the equilibrium formula. So we can use, so this S is now just the equilibrium entropy. Even though the full system is not equilibrium, each cell I can use this counting thing. Okay, so this does not even require local equilibrium or anything. It's just a counting strategy. Thanks. Okay, so this is the equilibrium entropy of an ideal gas, and I can compute for each microstate. I can compute what is the total entropy. And then if I okay, so these are the evolution of the fields, of these three fields with time. So maybe I won't discuss. Okay, so this is just to show that if I take a single realization but large number of particles, they show the same behavior as if I do an average over many realizations with the same initial macro state. Okay, so with increasing number of particles, these oscillations just go down, and you'll get something which is independent, which is the same as if you did an average. Okay, now for the entropy in this case, what we find is that again it has this log2 increase, but in this case it does not. Now I can again decrease this coarse graining size delta X or L, and here one finds that you get a convergence quickly to some size independent value, and the entropy just has this nice profile. Okay. Okay, so in this case it's monotonic and there are no oscillations. Okay, so this is very different, even though the initial and final values of entropy are exactly the same as for the other macro state. Okay, so this maybe I won't discuss much. If you do different initial conditions, for example, this is initial conditions where the particles are not chosen from Maxwell but from just each particle has plus or minus 1 velocity. Okay, so in that case the entropies never reach equilibrium, but if we put the slightest amount of noise to this, like if you take 1 plus minus epsilon, where epsilon is some random number, then immediately you get again same situation. Okay, so the entropy again reaches equilibrium. Okay, so let me go to now the case of interacting systems in the last 5 minutes. So this same system you can make it interacting by considering a gas where the alternate particles have different masses. Okay, so this is light, heavy, light, heavy, light, heavy, and this system and they don't cross each other, they just undergo elastic collisions which conserve energy and momentum. So this system is known to have good ergodicity and mixing properties, and in this case now you see that the evolution in phase space is completely different. You don't get these stripes and so on. This has lots of interesting properties which I won't discuss, for some time actually you can describe the evolution of these fields exactly by the Euler equations or of hydrodynamics. Now in this case again we can look at the same two entropy functions, and what we find quite remarkably is that both these definitions of entropy lead to the same, I mean, they agree completely with each other. So this, of course, is true in the large n and some limits which have to be taken carefully. Okay, so in this case, as you decrease delta V, we don't have this funny dependence on coarse graining for S, the first macro state, and both of them are just increasing functions of time. Okay, so we can also verify that this system is in local equilibrium at all times, and right, yeah. So let me now. Okay, so the difference in this case is that if you look at the Boltzmann's this equation satisfied by f, this function f in this limit, then it satisfies the Boltzmann equation with a collision term. And so in this case, entropy can evolve, okay? And this is usually what is essentially Boltzmann's H theorem. And what we are giving is a very explicit demonstration of this in a simple system, okay? And this fields, evolution of the fields also, we can write an equation where it's Euler equations plus some Navier-Stokes corrections. Okay, so so recently we are also doing this for a quantum case where it's now you can ask how do you do the analog thing in quantum systems. So there you start with a many-body wave function. Pavan, I have 1 minute.
Yeah.
Okay. Okay, so there instead of x we have a many-body wave function. Which we initially again choose from some thermal distribution, like it's a grand canonical distribution. We just choose one state out of this grand canonical distribution and then study how it evolves with time, right? And then we can again consider the same two macro states as we studied in the classical case, and we can do this counting and so on. Now, for the construction of f of this phase space distribution function single, this is a bit tricky in quantum systems because you can't really ask how many particles are there in each cell. So what we found is that okay, so one sort of usual standard thing to do is the sort of close analog of f is the Wigner distribution, but it is not positive definite and it's not a distribution really. So what we do is we find that you can sort of coarse grain this Wigner function and construct an object which is sort of tells us the number of which basically has the interpretation of the occupancy of some single particle basis states which are localized in both space and time. Okay, so this localization is of course up to some h cross limit, but so this is some nice construction that we can do, and using this construction we can now again look at exactly what we did in the classical case, and we find very similar behavior. We see equilibration at some time scale. There is a funny thing that because it's a system which has sort of integer quantum numbers, so there's an exact recurrence. So if you start from a half filled box, after this amount of time it again comes back to exactly half filled, okay, whatever initial condition you start from, but there's you have to look at the limit where you look at time scales much before that, and there's a limit where the system actually equilibrates, and then you can talk of all these things. So there are some other interesting things that the change in entropy is not log 2. For fermions it is between log 2 and 2 log 2, and for bosons it's always less than log 2. Okay. Okay, so I'll just summarize. I mean, so basically what I talked about is a demonstration of increase of Boltzmann's entropy during free expansion of an ideal gas. In the non-interacting case, I talked of two possible choices of macro variables, and both show thermalization in some sense, that at least what you are observing will seem to thermalize, and the final change of entropy is log 2 in both cases, with some differences. Okay, so I mean, one point is that things like ergodicity, chaos, and non-integrity are are not so relevant for observing irreversibility. This is one point that we want to emphasize. And what is most important is typicality of initial conditions and large numbers and coarse training. Right, and entropy increase comes because of our lack of knowledge of detailed knowledge of a system, and that's what is important. Then I talked about the interacting gas, and there we showed that because of mixing and local equilibrium, it ensures that these two entropies, macro state definitions, give exactly the same entropy at all times. Okay, so these are the references. Thanks.
In page number 12, you had 12 or 13 actually. There was a picture where you showed. This is the one actually. I mean, these types that you get actually after a while. Is it because of the initial conditions that you take for your configuration to start with?
For any initial condition, and at least if it's in this left half and you start with any velocity.
And then why this pattern appears actually? There is no particles with certain velocities between, let's say, 0.2
that's
to
because it's a non-interacting system and there's no mixing in the velocity. So the velocities are strictly preserved.
Yeah, but why there is a gap actually? That means you are not allowing certain particles having velocities between this.
No, see, I mean, okay, they're not parallel actually. There's a slight slope.
Right.
Okay, so I mean, if you look at any velocity, of course, has to be present, right? Initially, there's all the velocities are present, and here also all velocities are present, but they are just located at different spatial points. But if you, I mean, whatever velocities.
How do I understand this? These stripes actually. This,
right. Yeah.
How do you understand it? If there is no dynamics, why it chooses this particular one actually? Why not this wavy or something? Is there any, if I don't have any interaction between them?
See, I mean, the stripes, if you just take this small cell, okay, so what the particles will do here, okay, so they get reflected on, they all start with negative velocities. This is a wall. They get reflected and then they emerge from with positive velocities, right? And they're moving, see this minus 0.5 will get reflected to 0.5 and it moves here, okay. And then it just stretches, right? Because I mean, this guy at 0 won't do anything. It can just only stretch. And now when it hits the other wall, it will just emerge from this side, okay? So you can see that there can, I mean, because this guy, there can be no spreading of the velocities. Okay, if it was an interacting system, it would spread. This is what you see in the interacting system. But here, because there's no spreading, you will be left with these gaps.
Very interesting. Thank you.
So, yeah. Quick question.
So the previous slide, 13th slide. So you show that you starting from certain initial condition and the particular distributing, and you have a linear growth of entanglement entropy. So in the quantum case, there are ways to evade that. That is the localization you said. Is there any classical analog, like instead of free gas, if we take a disorder potential, like some potential very small, so will we have localization in place of like the classical thing? That means different way of growth of entanglement entropy.
Okay, no, see, this is not entanglement entropy. Like Boltzmann's entropy is completely different from entanglement entropy.
Okay.
So, and I said localization, but it's not localization like Anderson localization. This is just, I said you construct wave packets which are localized in space and time for a completely non-interacting system. Okay. So, it's nothing to do with Anderson localization.
So
if you put disorder, I mean, the situation will be very different, of course. Yeah, that will be, I don't know, because of course their thermalization is difficult and so on. In classical systems, you still have thermalization, but quantum it will be very different.
Yeah, so in the interest of time, we'll actually stop here and thank Abhishek. And, now there will be a switch over. Yeah, the next speaker is Jeremy Breck, and he's going to talk about relative dispersion of fluid particles in a turbulent flow, scaling and irreversibility. I hope this is the title. Yeah, it's the same.
try something. Maybe it's my adapter, which is out. Okay, good. Okay, shouldn't touch anything. Okay, so thanks a lot. Thanks to the organizers, so Pinaki and Arnab, and also thanks for your help so that I could get my visa on time. It was not a simple matter. So I'm going to talk about something which is a bit different from what Abhishek has been talking about. Namely, it's something where we don't understand anything about the dynamics, and we understand even less about what's happening when we do statistics. So it's I hope I will give you anyway some ideas. So I'm going to talk about the relative motion of particles in turbulence, and basically this is joint work with Giorgio Krostolovic from the observatory in Nice, François Lenen, who is now in industry, and Simon Talabar, who is at the University of Nice in physics. So motivations for this work is to try to grab some ideas about to quantify the fluctuations that one is observing, for instance, in atmospheric transport. So there are a few examples that I'm giving here. So from volcanoes to pollutions, transport of pollutions by the atmosphere, by winds, and the formation of clouds. So basically, there is something which is very important, is to be able to quantify fluctuations, and this is particularly important if one is interested in risk assessment. And so the thing is that usually when one is dealing with large-scale observations or models, which are unable to really tackle what's happening for the fluctuation at very small scales. So all of these problems have in common the fact that they are transported by a turbulent flow. So a turbulent flow is what I will be considering is an incompressible solution to the Navier-Stokes equation. So which is in a steady state, a statistical steady state. So which means that they have some, it's a force dissipated Navier-Stokes equation. So with a random forcing which is injecting kinetic energy, and some dissipation which is occurring at small scales. And of course this is one of the most famous out of equilibrium system, where basically we know that the energy is flowing over the scale. So when we are injecting too much energy compared to the speed at which it's dissipated, basically we obtain what is called the turbulent state, where basically the energy is flowing from the large scale where it's injected to the small scales where it's dissipated. So the thing I want you to remember from this picture is that everything is getting smooth at small scales, so that there is a scale which is called the chromograph dissipative scales, below which the flow is smooth, is differentiable, and has a unique time scale. And in between the large scale where we inject energy and the small scale where it's dissipated, we have what we call the inertial range, so in this intermediate asymptotics, where we assume that the energy is flowing, is going through a cascade. So these are the ideas of Chromograph in 1941. And in this, for velocities in this inertial range, what we observe is that they have a behavior such that the increment of velocity is going like the power 1/3 of the separation. So which means that now we are no more smooth, so we have something which has some kind of scale invariance. And associated to each of these scales, I mean we can each of these length scale and velocity scale, there is a time scale which is given just by the turnover time at this scale, which itself goes like the power 2/3 of the scale. Okay, which is just the turnover time, so which means the space length, distance divided by velocity. So now, when we are interested in turbulent transport, basically, we are looking, coupled to this Navier-Stokes equation, to this velocity field, to the advection diffusion equation, which is written here, where we assume that we have a scalar field, some concentration, temperature, something, so the amount of pollutant we have, which is transported by this velocity field and has no feedback. So we neglect any feedback from this scalar field to the velocity field. So it's just a passive scalar. And so now, if we try to understand somehow what are the length scales of the mixing inside this equation, there is something which is, again, very old, from the 50s, which is called the Batchelor scale, which is the scale at which, below which, the diffusion will start to act. So, okay, so if we are below this scale, I mean, the dominant term in the advection diffusion equation is the diffusion term, and then everything will diffuse, will get mixed. And so when we are interested in quantifying fluctuations in transport, I mean, we want to understand exactly how this diffusion is helping to make things smoother and mixed. So now, typically, if we look at applications, so in atmospheric conditions, typically the chromograph scale, so this eta, the scale below which the flow is smooth, is of the order of 1 millimeter. So that's typically the scale that we are interested in atmospheric flows. And so now if we try to estimate for some kind of pollutants, so for instance ozone or aerosols in air, what will be the corresponding Batchelor scale, I mean we have things which are very small, like of the order of a millimeter for ozone, or even of the order of 1 micrometer for aerosols, which means that diffusion is useless in this game. That diffusion will just mix things on very, very small scales. So turbulence will be very important, and so now the usual way to try to estimate the effect of turbulence is just to think. So this time at the concentration field in terms of the characteristics to the advection diffusion equation. So we look at solutions to the differential equations given, so to the stochastic differential equations, where we have velocities of the particle is given by the free velocity at the particle position plus some diffusion with the proper diffusion coefficient, and now what we know from typical stochastic equations is that the advection diffusion equation is nothing but the chromograph equation associated to this stochastic equation. So now if we make some average with respect to initial data, okay, so we assume that so average condition on initial data with respect to the stochastic noise. So what we get is that we can express at any position and time the concentration field as the average of the initial data along these stochastic equations, which are ending at a given position. Okay. So now, clearly, so above this bachelor scale, advection is dominating, and what we have to describe what's happening is usually the usual Taylor approach to turbulent diffusion. So we can use now the equation for the characteristics in order to write some kind of a Green-Kubo formula, where we obtain that the typical square displacement, can be written as the time integral of the velocity correlation along the path of the tracer. Yes, please.
So I can follow what U is actually.
U is a solution to Navier-Stokes. It's a prescribed velocity field. Okay. Which is supposed to be turbulent, which means that it has some scale separation between the place where energy is injected and the place where it's dissipated. So now, basically, one can try to treat, to rewrite this time integral of the correlation at very long times, okay, to get the leading order things at times which are much longer than any finite correlation time. So assume that there is a finite correlation time, and then what we get is, so this is the usual way to get some diffusive behavior at large times, and what we get is that we have some effective diffusion acting on very, very long time scales. So this means that there is a kind of mean field equation that we can write for this theta field, which is just a diffusion equation with this effective diffusivity, which is given by the typical variance of the velocity and times the correlation time, the integral correlation time of the velocity along path. So now this mean field approach is in principle can be used to get the mean concentration, and this is what is done in applications. And so here what you see is an example of some tracers, some pollutants which are emitted from this source, and which are then transported by a flow, and this flow is turbulent and has a mean velocity toward the right. And what you see as a background color is the solution to this effective diffusion equation, and which in principle is describing, so it's what is called the Gaussian plume, because it's giving a Gaussian solution, and which is in principle useful to get the mean concentration. But now, as you can see from the dots, which are the instantaneous positions of particles which are emitted from this source, what you see is that you have very strong deviations from this mean, and this is what we are willing to quantify. And so now what I will discuss is that actually the spatial correlation that we observe in the actual density can be related to the relative motion between two particles. Yes?
It does not satisfy the diffusion that it does not follow the diffusion it doesn't satisfy the diffusion.
So the diffusion equation will be the background, and in principle this is okay to get an idea of the mean concentration average over time, of the full average. So if I were taking different times of this for this instantaneous distribution, averaging over time or ensembles, etc., basically I will get something which is very close to this mean field. Indeed, it will be okay. So now, again, so using the relationship between transport of the scalar field and motion of the characteristics. So basically what I can do is write again in the same way the correlations of my scalar field, with this time I can relate them to the initial correlation of my scalar field at time 0 times the transition probability. So basically if I'm interested in the correlation between x and x plus r, basically I have to average over all possible position x01, x02 of two tracers, times the transition probability that at time t I have one tracer at x and the other one at x plus r, knowing that initially I had one at x10 and the other one at x20. So it's just the 2-point transition probability, which is just something which is given by the flow. Okay. and the diffusion, of course. So now the thing is that, so what it means that if you look at time t, basically you have a position x plus r, basically you have to average over all possible transports that are leading to these 2 points. So all possible trajectories where the fluctuations is coming from diffusion. And now, if we assume that we are homogeneous isotropic, basically, I will not talk about the full vectorial transition probability, but just to the probability that I'm having 2 particles at a distance r at time t, knowing that initially they were at a distance r0. Okay, so it will simplify a lot the other ways. So how is it a 6 times 2? So it's a 12-dimensional function. So now, and then I can do, of course, the same kind of trick if I'm interested in higher order correlations, looking this time to the n particle relative motion. So now what is known from this approach is that basically scalar mixing, fluctuations, and even the dissipation of scalar are fully determined by this 2-point distribution, and this is what I'm going to discuss in turbulent flow. And in particular, there is something specific. So this is a snapshot of a numerical simulation of a scalar transported by turbulent flow. So there is something very specific appearing in this transport, is the apparition of shocks. So places where the scalar is varying very abruptly on a very small scale. So which means that it's corresponding to almost infinite gradients. And these very large gradients are the place where the scalar is dissipating, okay, a lot, where diffusion is acting a lot, if you want. So basically, all these fronts, as you see, they correspond to having 2 trajectories coming from very different locations, coming together in a finite time, almost together. Okay, so again, fully related to the properties of this 2-point transition probability.
Is there a probability that the particle which is evolving as a function of time can also have a vector in the opposite direction? Meaning, because of the fact that it's a turbulent diffusion, would you always have evolution in one direction?
It depends on your conditioning, actually. I will talk, it's next slide more or less. so basically now assume that we are interested in the relative separation between 2 particles, each of them being just a solution of the characteristic to the velocity field given by Navier-Stokes. And now, basically, depending on the initial separation and the time at which, so initial separation, it means that we are conditioning on something at time 0, which is this initial separation. And then we observe the separation at time t. And depending on these 2 parameters, we have different regimes. Okay. So the first one, which is the easiest to understand, is that if you fix some given initial separation, so each particles have a velocity. So initially, they will just go a ballistic motion. Okay, so because they have a velocity, this velocity has a finite correlation time. So they will just move, keeping their velocity, so they will just separate ballistically. And this is this yellow region. The second thing that you can understand easily is what's happening when you make the 2 particles infinitesimally close to each other, at scales where the free velocity is differentiable. In that case, basically, you can linearize the separation between the 2 particles, and what you get is that they separate exponentially fast, with the Lyapunov exponent, which is given by the Lyapunov exponent of the tangent system to the linearized dynamics. I mean, to the equation of characteristics. Then the thing I talked about was the diffusive regime. So this exponential separation is the blue thing here. The thing I talked about is this diffusive regime. So when you are looking at timescales which are much longer than any timescale in your flow, then of course things are diffusing. So it's basically this diffusive regime there. And then I will be more interested in another regime which is in between here, which is the so-called explosive regime, where typically the average square distance between particles is growing in a super diffusive manner, and actually like the power 3 of time, with a constant, a coefficient here, which is independent of their initial separation. So that's why it's explosive. But diffusion is also explosive. So basically, if you have two diffusing particles, they separate in a manner which is independent of the initial separation. But now, so you can make them at the same location and they will separate. So now, of course, the ballistic regime and the exponential regime, they have a dependence on the initial separation. And this regime, this so-called explosive regime, is independent of this thing. So how to understand this stuff is basically, as I told you, when we look at scales inside the inertial range of turbulence, the velocity field is losing its differentiability, and it's only Hölder continuous with the Hölder exponent, which is of the order of 1/3. As you remember that velocity increments in turbulence, they go like separation to the power 1/3. So which means that if you look at this equation with such a non-differentiability, basically you're losing uniqueness of the solutions. So just assume that, for instance, that you are looking at an equation like dx dt is square root of x, or x to the 1/3. Basically, you have two solutions. One which is x equal to 0 at any time, and the other one which is x going like a power of time with the proper power. Okay. So this is so basically we are losing uniqueness, and so this loss of uniqueness has been coined spontaneous stochasticity, because of the following thing. So now assume that in this equation I'm adding some way to regularize the velocity field. So I make it smooth at small scales. Okay. So which would be corresponding to take a finite value of a given parameter, nu, which is my regularization parameter. And now I can now construct fully the transition probability for my flow defined by my characteristics. And so what is spontaneous stochasticity? It corresponds to taking the limit when this regularization parameter is going to 0, and then the limit when the initial separation between the particles is going to 0, and then to look at the behavior of this transition probability. And what's happening is that this transition probability is not going to a delta function. Okay, so this is the probabilistic way to understand non-uniqueness. So uniqueness would be just for a given R0. I mean, I will get, so of course it should be vectorial this time. I will get a unique solution, so unique R times T. So which will mean that basically my transition probability will go to a delta function. And so now, even if we don't have any source of noise, the only idea of having something which is non-Lipschitz and giving something non-unique is implying that we always have a signature of any way we had to regularize the problem, and always something which is becoming spontaneously stochastic. Okay, where particles will separate even if there is no noise. So what does it mean? It means that, as I was telling you, it means that you have this explosive separation that basically this is known for a long time in turbulence, and so it's called the Richardson law or Richardson-Obuchov, and which is telling you that the typical, the average square distance is going like the cube power of time, with some dimensional parameter epsilon, which is the energy dissipation rate of your turbulent flow, because it's just dimensional way to non-dimensionalize this, and a constant g, which is supposed to be universal, which doesn't depend on the kind of flow you're considering, neither on the Reynolds number. And this occurs for times which are much bigger than the typical turnover time, typical time scale associated to the initial separation between the particles. So what does it mean also to have something which is explosive this way? It means that mixing is infinitely more efficient than in a chaotic flow. Okay, turbulent mixing, because of that, basically you can bring things far apart, put them together. Okay, and which means that you don't need the time which is given by the Lyapunov exponent in order to mix things. I mean, it can take just a time one. independently of the initial the kind of gradient you're expecting or the initial data that you have. So now there is a difficulty with this law is that it's hardly observed neither numerically nor experimentally. And this is mainly because it's requiring a very large timescale separation. So the kind of timescale separation is, so you need this time associated to the initial separation to be large enough, so basically to have a turbulent behavior, so to be larger than the small time scale you have in your flow. Then you need to observe the separation at a time much bigger than this time associated to the initial data, to the initial separation. And this time of observation has to be much smaller than the large scale time, otherwise you have just pure diffusion. Okay, so it's intermediate asymptotics, which has a lot of constraints. So for that, in order to look at things a bit further, so this is typically what you get with not too cheap direct numerical simulations. So basically, it's direct numerical simulations of the forced Navier-Stokes incompressible Navier-Stokes equation using 4,000 cube collocation points, and these are typical measurements of the square separation between particles as a function of time. So it's rescaled in a way that you observe that the ballistic regime is collapsing independently of the initial separation, and that at the same time things are going to the explosive Richardson regime, again collapsed on the same curve, on the same master curve. And so what you see is that, so you can trust it a bit or not, what you see is that you barely observe a decade of T-cube scaling, and only for very specific initial conditions, which are initial separations, which are a bit close to the dissipative scales. So now, basically, so there are ways to try to quantify further, this behavior. So now we know that R square is going like T cube. And so basically, the old ideas of Richardson, so which has almost 100 years old, which was almost 100 years ago, basically is to assume that the velocity differences are uncorrelated. Okay, and basically, then you say, if that's the case, you just say that the separation is diffusing, so you can write a Fokker-Planck equation for the transition probability. And this Fokker-Planck equation is something of this kind where the diffusion operator, which is here, depends on the scale. Okay, so it's like the Fokker-Planck equation for multiplicative noise. And the way it's depending is just given by a dimensional analysis. So you want to construct a diffusion operator which depends only on the scale and on your turbulent property, which is the dissipation rate. So the only way you can write it is like the power 1/3 of the dissipation rate times the power 4/3 of the separation. And once you are assuming that it has this self-similar shape, then you can write everything and show that at very long time your 2-point separation will take this scaling form. So something where basically there is a power, the proper power, and an exponential of the scaling variable. And of course, you also obtain that the variance of the distance is going like T cube in the scale. So now this kind of approach has been formalized only in one case, which is the case where we indeed assume that the velocities are uncorrelated, which is called the Cracknell model, which was basically introduced by Cracknell, studied a lot by Gavensky, Vergasola, and many others during the late 90s. And so in that case, of course, what you assume is that the velocity field is not a solution to the Navier-Stokes, but it's a prescribed random velocity field, which is Gaussian, white noise in time, and with specific correlation in space, which is a power law. And then, if you assume that, you can show exactly that what you get is indeed a diffusion equation. I mean, of course, you have put all the ingredients, so it's not very complicated. And that basically you get the right scaling form for the two-point distribution. Now, if we now try to think about what's happening in an actual turbulent flow, I mean, there is a clear shortcoming, is that basically actually the velocity difference that we have at a given time t has a typical time scale which is of the order of t. Okay, so typically you can see it this way. So I told you that the typical time scale at a given scale r is like going like r to the 2/3. If in addition you assume that r square is going like t cube, then it's clear that the correlation time of the flow that you have at a given time t is of the order of t. Okay, so which means that there is no way you can get some asymptotic argument to say that you have diffusion of distances. Sorry. So now, and in addition, so now if you do some measurements, so these are measurements of the two-point probability the transition probability for different values. I think I lost. It's weak. It's here. So for different values of the initial separation, and so basically it's represented in such a way that if things were exactly obeying the Richardson scaling form, it will be just the dashed line which is shown here. And what you see is that you have clear deviations. In particular, you have broader tail at small distances, which means that there is some kind of trapping occurring at small distances. And then you have a clear dependence on the initial separation at large distances, which means that things which are so that there is some kind of memory effect, that if you have started from a large distance, you're more likely to go to a larger distance, even if it's just a relative distance, than if you were starting from smaller distances. But at the same time, I mean, this is the typical way people are representing things. But I mean, it's people are cheating a bit, because you see that by using this rescaling, actually you're pinching all the data here and there. So which means that you pinch them, and then you try to pinch them at 2 points and try to make them look like a line. So it's not very fair. But still, we see deviations. So now there has been other ways to try to tackle these deviations, so which were based on assuming again that the separation is Markovian, but this time it's not the velocity which is diffusing, but the time derivative of the velocity. So you go to next order. So what you assume is that now the time derivative of velocity is some kind of, so in principle it's the acceleration, so the difference of acceleration in 2 points in the fluid. And what you assume is that this acceleration is correlated on small time scales, because you have small eddies which are making things going right, left, etc. And that you can assume that you can replace this this acceleration by a white noise, by using some kind of central limit theorem. And so now what you get is a coupled equation for the separation, which involves the velocity difference, and the velocity difference, which is now a diffusive process. And then you can write a Fokker-Planck equation, this time for the joint probability transition between separation and velocity, okay, which is like that. And then you have to assume something in order to close your system. So this is going more and more like engineering modeling, and the way people are doing this thing is they put this so-called well mixing condition, which is the following: is that now if you assume that this is supposed to describe something for your flow, you can take solutions to these Fokker-Planck equations which are assuming that the initial distribution is uniform. So as it's uniform, it's incompressible, so things are staying uniform. And now, if you make if you look at velocity statistics with this distribution which is uniform in space, basically you should recover the usual velocity statistics of your turbulent flow. Okay, so this is the way people are giving constraints on these models. So there are many limits to this Markov modeling. So basically, the first thing is that actually acceleration is not really short time correlated, and in particular, so it's okay for the components because typically so some free particle when in a flow will turn a lot. So will be in an eddy, so it will turn a lot. So basically, components are getting uncorrelated very fast. But if you look at the amplitude of the acceleration, I mean, what you observe is that it's a long-range correlated process. This amplitude of acceleration. The second thing is that basically the most models they are leading asymptotically. All of these models they are leading asymptotically to Richardson diffusion. But what we know is that Richardson diffusion is not. I mean, the distribution of the transition density distribution is not described by Richardson. So this is a problem. And then the other thing is that there are many other observations which are telling you that you have some memory effects, and that things like Levy walks or waiting time approaches are giving some better estimates of the relative separation. So basically, I will try to talk quickly about another type of scenario, so which is where basically we are breaking Markovianity, so where we assume something non-Markovian. And this scenario consists in considering that a pair of particles in a turbulent flow is going a sequence of independent ballistic separations. So the model is very simple. So we assume that the separation is given at time n+1 is given by the initial separation plus delta t times some velocity difference at time n. So it's just this is one piece of the ballistic motion. But then the time it takes to the next time step is also a random variable at each step. So it's in the framework of the continuous time random walks. So basically what we assume is that of course the time step, the velocity steps and the time steps are dependent on the separation, on the given separation. Okay? We will plug the turbulence scaling that we know, turbulence statistics. And what we also assume is that the delta u's, and the delta n's are independent from each other. Which will mean that in the Rn Tn space, this will be just a random walk. But then it's when we want to reconstruct the actual time. So we need to sum up to condition on Tn that we will lose Markovianity. So this is a usual trick to deal with some easy non-Markovian system. Perfect. So now the thing is that, so with such a formulation, so basically what we assume is that the velocity step is something like the power 1/3 of the spatial step, that the time step is like the power 2/3 of these things. And now what we assume is that these are things which are these power laws are just the way things are depending on the separation, and then we just multiply these values by a fluctuating Gaussian unit variance random number. So the first remark is that assuming that we have something of this kind, so which is the case here, means that actually it's not really powers of R which are relevant, but it's more the logarithms of R. Because you can see that if you write, so with this formulation together with delta U and delta T being like that, you see that delta U times delta T will be just power 1 of R, okay? And so which means that you can write the evolution for R in this way. And so which means that at the end you just have a multiplicative process for R, so that you can write the log of R as maybe a sum of independent variables. Actually a sum of independent variables if you assume that they are independent, and which means that it will grow like n. Okay, so it's more the log of separation which is diffusing rather than some separation to some power. The second point is that you can easily see from here that again, assuming this kind of scaling for delta t, that you can write time t after n step as an exponential of something times n. Okay, so which means now that n, you see, is log of time from that. So which means that log of r will grow like log of time, which is the thing we want for power laws. And so putting all the power together, actually, you get that the log of the ratio between separation and initial separation is 3/2 log of t by t0. So which is the same scaling as saying that r squared is going like t cubed. So now we have tried to understand whether this log of separation is indeed a self-averaging quantity. So is following this central limit theorem, if there is or not, and if there are large deviations. So what is shown here is again data from numerical simulations. So this time it's a bit different because I'm sorry, no, it's okay. So here what is shown is, so what I call rho is the log of the separation in distance, and what you see here is the average rho. I mean, these are the field symbol here as a function of log of time. And this dashed line here will be the t to the 3/2 scaling. And the second thing is the standard deviation of this rho. And what you see is that the standard deviation as a function of time is going to saturate at some point. So having the mean growing and the standard deviation saturating is something which is in the line of law of large numbers and central limit theorem, because the standard deviation is rescaled the proper way. And so now we can understand better. We can try to understand better this model. So we rewrite it in the following manner, with alpha n and beta n's being some random numbers. Okay, so you remember it's a multiplicative thing for r with some numbers, and these numbers are not independent from what's happening for time. And so now, basically, there is a specific change of variable where we remove the mean of log of r that allows us to write a single equation for this gamma n. And basically, the thing is that this new variable gamma n is becoming a stationary variable. So we are able to show that in this model. And in particular, the process of doing it is that we can see it from this gamma n dynamics. Basically, gamma n as a function of step is fluctuating this way, and its dynamics is such that it's bounded. So there is gamma n equal to 0 is forbidden, so it's never going to gamma n equal to 0. So gamma n are always staying negative. And then when your gamma n is very large, there is a drift acting with a positive slope, which is becoming larger and larger, which push you back the gamma n's inside this thing. So this is the mechanism which is making the distribution of gamma n stationary. Yes, alpha, beta, and random variables. So beta is positive, but alpha is not. Yes. So beta is positive because alpha is somehow how much how big is the component in the separation between trajectories. I mean the longitudinal component compared to the full norm of the velocity difference. So this is the alpha. So parallel means that it's delta u projected on r. And beta n is delta u cubed by r. So and it's something which is always, I mean, it's modulus of delta u cubed by r, and it's something which is always positive. So and for this specific case, I think it corresponds to alpha n uniformly distributed between -1 and 1, and beta between 0 and 1. And they are bounded. We assume bound. I think that so alpha is clearly bounded because it's between -1 and 1, but we assume beta bounded, but it doesn't matter much. So anyway, so through this approach, basically, we indeed obtained that the mean separation is going like 3/2 of the log of time plus some constant that is just the mean of this reduced variable gamma. And this constant is important because it's the thing which is giving the constant in the power law for the separation of distances. Then that the variance is a constant, and that the PDF is some function only of this rho minus. So now back to the PDF, and I will finish on that. So basically, so now that that we propose this other scenario, which is a scenario on which is telling us that it's the distribution of log of r which is important, and not the distribution of r squared divided by t cube. Basically, what we have done is to now show the distribution of separations between tracers. This time in terms of the log variable, instead of taking some r to some power, etc. And so what you see now is that for the data corresponding to different initial separation collapse better on the top of each other. So of course there are some deviations in the tails there and there. So Richardson diffusion scenario, I mean the distribution coming from Richardson diffusion is the dashed line here, which is now again a single curve in this rescale variable, but now it's clearer that one observes deviations both at small separation and large separations. And finally, what you observe is that for given values of the parameters in our model, we are able to obtain something which is well reproducing the master curve on which actual data is collapsing. But we have no way to explain how to choose these parameters. And I will stop here. Thanks.
So we have time for maybe a couple of quick questions. Yeah. Maybe I'll ask my question. Is there a possibility that you actually can also have fractional exponents when you're making this transition from, let's say, from an explosive to other regimes, or vice versa?
Of course, I mean this was in the open questions that I wanted to discuss. So basically the problem of turbulence is that we have anomalous scaling. So depending on what kind of statistics, I mean, we have different exponents. So here things seems to work well with the Komolov things, but when one is looking at different statistics, like exit times, so if you look at the time needed for a separation to double, for instance, then the scaling is completely different, and one has a signature of this anomalous scaling of turbulent flow, which is very strong. So that's one open question.
Yeah, because the time scales at which you will have to do these measurements also are quite challenging, right? Because if you want to measure them, is there any advice you give for experimentalists to look at this signature in a specific way, by any chance?
Exit time is easy, actually. So exit time is a good candidate to make finer measurements, rather than just diffusive property. I mean, to look at exit time or doubling time for a given distance, and as a function of the initial separation, of course.
If there are no more questions, let's thank Beck for a very nice talk.
Thank you.
And we'll break for coffee and regroup at 11:30 sharp.
substance is liquid-like and the consistency at rest is like a paint. You see, rather than creating a splash, this heavy object is bouncing off the surface. Okay? So as if the force is transforming this system into a solid transiently. Okay? And same principle allows one to run across a pool of cornstarch. You can see like many YouTube videos. So this compressive force is not a requirement. One time people thought that it is the compression that solidifies the system. Actually, there is one interesting video that one guy got inside this pool of cornstarch. He has a difficult time getting out. See, that means it can resist the extensional force as well. Okay? So few years back we studied this problem in a more systematic manner in the lab, like all kinds of jamming under compression under extension, and we showed that actually basically why this is so common and works for any kind of deformation, because this jamming is basically shear induced. As long as you have velocity gradient inside the system can jam, and this we demonstrated more clearly, like you take a beaker, that is this glass beaker, okay, you keep dense suspension, cornstarch and water for example, and you have a inner cylinder that can spin very fast, okay. So you see that so now by spinning the cylinder, you can create a velocity gradient without any compression or extension. You see like the shear can actually solidify the system, and if you stop shearing, it becomes goes back to initial fluid-like state. Okay. So due to this interesting property, these materials are being used as in various designing flexible shock absorbers. These are few examples. So you take this Kevlar fabric, which is the material we use for making this stab and bulletproof vest, and you treat it with dense suspension. You see like it becomes very tough. It cannot be punctured without compromising the flexibility. That is important, because you can argue that why not a steel plate, because it won't be flexible and it can bounce off bullets and all, and also you can see it is deflecting of a hunting arrow, which is like almost more powerful than a bullet probably. Okay, and there are other potential applications as summarized in this recent review. Okay, particularly in the field of designing flexible shock absorber. Okay. So now, despite of this study, there are many open questions. For example, actually the mechanism for shear-induced jamming is not well understood. So the questions like what sets the upper limit of the stress response after perturbation, how quickly one can get to the jammed state. Once the jammed state is formed, how quickly it can relax. So if you realize, like such questions are also very important for application perspective, because if you want that, okay, some solidification required over within this time scale, so all these questions become very important. So in this, here I'll tell you about this shear-induced jamming under transient perturbation that is relevant for the examples I have just given. And I'll particularly focus on microscopic particle scale dynamics that is giving this the relaxation of shear jammed state that has not been explored before. Okay, so just I'll take a step back. Now, how do we quantify experimentally such material? So you use a technique called rheology. So you take, for example, you confine your system between two plates, and you apply some force, shear force on top of, on one of the plate. In this case, it is the top plate. So now you can define these two quantities, the stress and shear rate. Stress is simply the shear force divided by area, and the shear rate is the steady state velocity that is produced as material response divided by the gap. Once you know this quantity, the ratio is viscosity. So different materials like, for example, water, oil, honey, they have different viscosity. But one important thing is they are all Newtonian. That means that their viscosity is independent of how much force is applied to measure the viscosity. Now, coming back to dense suspension. So dense suspension is quantified by the solid volume fraction. Now at very high volume fraction, typically approaching random close packing for Hertzsprung system, for example, if you have interactions, it can go down. So it becomes highly non-Newtonian. That means the viscosity now becomes force dependent. So this is a illustration. For example, for the same system, I am going to tell you that when your volume fraction is fairly small, 0.45, 45%, you see that the behavior is almost Newtonian. There is some increase in viscosity at high stress, but as you increase the volume fraction, you see very strong increase in viscosity and also some decrease in viscosity at low stress. So this is highly force dependent. Okay, so in the steady state, like how do we understand such response? The reason is the following. So this shear thickening or shear jam system, these are well dispersed systems. So you have high density of particles, but they are well dispersed. Now contact between the individual particle at rest, those contacts are weak, and those are lubricated contacts. Now as you increase the applied stress, shear stress for example, so some of these lubricated contacts transform into frictional contacts, that is indicated by red, and finally, like at high enough stress values, you have enough frictional contacts between the particles, so average number of contact is very high, and so the viscosity can increase or it can go to even solid-like state. And this evolution of contact for a wide range of system is given by this given by a model proposed by Mike Katz and Matthew Weird. It basically tells like how the force is transforming, what fraction of contacts are transforming into frictional contact under force. Okay. However, one thing is there is no information about the dynamics of contact formation or relaxation. We know that, okay, if you have so many contacts, this will be the stability, but how the contact is formed or how the contact is relaxing, that is not there in the model. So now what we study is a dense suspension of polystyrene particle dispersed in a non-evaporating solvent, that is polyethylene glycol. And these particles, since we require large amount of particle, we synthesize these polystyrene particles, which are like around 2.6 micron with a fairly small polydispersity, about 5%, in the lab by a technique called dispersion polymerization. So we make the dense suspension out of them. Now what is the experiment? We again confine the system between two plates of rheometer, and we apply a transient perturbation in the form of this tape. We apply a step strain, and then we observe the stress relaxation in the system. So this is the result, what we get. So you see very fast you get to a fairly high peak stress, and the stress relaxes. Now these are for different amount of step magnitude. As you increase step magnitude, it is the peak stress increasing, and also the relaxation time increases. So and the feet, these are strong. This relaxation is strongly non-exponential. So we tried various functional form, but we found that for different volume fraction, this is for volume fraction of 58%, if I remember correctly. So for different volume fraction and strain values, this is the most general form we can fit the function. This is a power law cut off by this stressed exponential, or rather compressed exponential, because beta value, most of the cases we find it is bigger than 1. Okay, so similar functional form is observed in simulation for dense frictionless system close to jamming in these papers, but their connections are not very clear, so this is what we have tried. Now, one thing I'd like to point out that now if you go to higher value of strain, a very interesting thing happens that you get to high value of peak stress, but then you develop this two-step relaxation. Basically, you can see that this step is quite significant, almost one order of magnitude. Some at higher volume fraction it can be even more. So this is a log-log scale. So if this axis is linear, actually this is the most significant relaxation. Most of the stress relaxes during this step. Okay. So we can define two time scale. One is starting like up to the first step that we call the first time scale, and second one over which starting from this point when the stress relaxes to almost zero, we call that slow time scale, tau s. Okay, so this is the same data basically. So here I am showing the two-step relaxation separately for different strain values. One thing I would like to point out that this is the first normal stress difference. So what is that? So you are shearing the system this way. So you are measuring the shear stress, but because it's a complex system, it can develop some force perpendicular to the shearing direction also. It can be like compressive, it can be positive or negative, the normal stress. So typical signature for shear thickening system, which is very close to random close packing, it gives positive normal stress under steady shear. But here, if you look at the normal stress response, you see when the shear stress is very high, the normal stress is not that high, and it is actually random. For different volume fraction, it can be close to zero and so on. But when the shear stress drops, you see like there is a peak in the normal stress, there is a second peak developed. So that's why this transient response is quite different from the steady state one, because in steady state, the normal stress and shear stress response for this system, they go hand in hand. Actually, as shear stress increases, normal stress also increases. Just to illustrate the difference, that transient response is quite different. Okay, so now how do we understand further like this complex relaxation process in the system? Okay, so one property of this shear thickening dense granular system is like I told you about the normal stress. The normal stress in this case is generated because as you shear the system, you have to maintain some velocity gradient. That means different layers of particles, they have to go over each other. In the process, in that dynamic condition, there is an overall soiling of the pack. This is called a mechanism called frustrated dilation. And so it is soiling not only in this direction, in all direction. Now this side you have plate, we cannot see anything, but this side you have this suspension which is like, it has some solvent and this is the air, so solvent air interface. So you can see that as we shear it, the particles dynamically protrude out. So these are granular systems, so this gap between the plate is about 1 millimeter and the particles are fairly big, like it is around 120, 130 micron in diameter. Okay. So this soiling or dilation competes with the air-liquid surface tension, and what it results in is change in surface texture basically. Okay, so this is one aspect, and there was earlier study by Brown and Jaeger. So they showed that for a wide variety of systems showing shear thickening and jamming, this surface tension provides a confining stress. This gamma is the surface tension and A is the diameter of the particle. So they found that this maximum stress one can obtain by shear thickening is given by this gamma divided by A, but it is not exactly that. There is a prefactor of 0.1. Okay, so although the data is fairly scattered, but you can see there is a rough trend in the data. Okay. Yes.
The sample between two plates.
Yes.
So where is the air liquid interface?
So at the edge of the plate.
Just at the bottom.
Yes. Yeah. Yeah. So this is the actual experimental setup, schematic of the actual setup. So we have this top plate. Actually, it is a cone because of the reason I can tell you later. And cone with very small angle, and there is a bottom plate. So we are using a counter rotation. The plates are like rotating in opposite direction. So these particles are opaque, so the suspension looks whitish. So what we do, we illuminate the boundary and we capture the image with a camera. So this is the actual setup in the lab. These are the two plates. So you put the sample and bring down the plate to confine the sample. Okay. So because we are driven by the fact that we are expecting that when this jamming happens, there will be some change in surface texture. That's why we are having this kind of experimental setup. So see what we get basically. So this is the top plate and this is the bottom plate. Scale bar is 100 micron. So you see this is the static interface. It looks like how it looks like. So after this step shear, you see that these white spots developing and they quickly disappear. Okay, and then see like there is this brightness is gradually changing. Okay, so I can play the movie. I can go back. Yeah, once more. So these white spots. Okay. So these white spots are, we call it plastic center, and this brightness that we are getting, this is due to dilation, which is relaxing also. Okay. So now why we call the white spots as plastic center? Because what we found is like if you apply sufficiently high stress, these white color spots, if they merge, they form this line and eventually that creates a fracture. Okay, so that means like the individual ones, they might be like small local plasticity. So one problem is like, see, we can see the particles as it will be clear in the next movie only when they dilate out. After like stress drops, the particle goes inside the bulk, it is difficult to see. So this is again the same movie but with a better resolution where you can see the individual particle. You can see that there are these plastic centers near the peak stress and the plastic center goes away after the first step. But the other particles, it takes longer time before the intensity drops to the initial value. Okay. So now what we did, we tracked many such bright spots, for example this one of these spots, and plot their intensity as a function of time. And also we study the intensity variation in other region which doesn't have a bright spot, but it is the brightness just increased due to dilation. Okay, so for example a region like this. So you see like where this bright spot is there, the intensity relaxation shows us two-step behavior, right? There is a first step and there is a second step, whereas for the other region, it takes a single step, single relaxation, and we define two time scale. One is this tau p, because these are the plastic center relaxation time, the first step, because I told you that after first step the bright spots are gone. And second relaxation is the dilation relaxation. So we tracked many such spots and we can get a distribution of time, and you can see there is a clear separation that plastic center relaxation is happening over much shorter time scale than the dilation relaxation time. Okay. So one more thing we did, it is based on the difference image, what it is telling us. So suppose you have some image of the boundary. Now you take at some time, image is taken at certain time, and then you take image of the same region at a different time, delta t. So time difference between them is 16 millisecond in this case. So the idea is, if we subtract one image from the other, if these images are different, then you get some intensity in the difference image. That means that there is some rearrangement has happened. Suppose this image is completely static, then if you subtract the same image from it, then you get zero intensity basically, because you are subtracting same thing. Okay, so same thing we do with almost similar time separation, but during dilation, you see this absolute time is little larger. That means it is beyond the first step actually. So we calculate the difference image. So these are the images. So you see that during the plastic center relaxation, if you take a difference image, you get very localized rearrangements as shown by these bright spots. There are some small rearrangements happening, but these stands out basically. Whereas during dilation relaxation, if you take difference image for almost same delta t, you see that you get a system spanning relaxation, because everywhere this difference image is showing bright spot. Okay, so everywhere the reorganization is happening. Okay, so now we compare this time scale that we obtained from the rheological measurement. Remember, like I indicated, this fast and slow time scale based on the stress relaxation data, and also we defined this time scale for plastic center relaxation and dilation relaxation. So now for wide range of volume fraction showing this shear thickening and jamming, you see that the fast relaxation that is obtained from stress relaxation from bulk rheology measurement, it matches exactly with the plastic center relaxation, the fast relaxation process. Whereas that slow relaxation time matches well with the dilation relaxation time. So we get very good agreement between these two. So this indicates that fast relaxation is due to localized plastic center relaxation, and slow relaxation is coming due to system spanning dilation. So to verify this further, what we did, we also changed the solvent viscosity. Okay, so we are using the same volume fraction, but PEG, it's a short chain polymer basically. So depending on the molecular weight of polymer, you can increase or decrease the viscosity. So you see that, oh sorry, so this nothing has been in it. Okay, so this fast time scale, this is independent of solvent viscosity, whatever variation we could achieve. Whereas dilation relaxation, with increasing solvent viscosity, the slow relaxation time increases also. Okay, and together with the last plot that I showed, so we concluded that this slow relaxation time increases with increase in solvent viscosity and particle volume fraction, whereas fast relaxation time is pretty much independent. So it supports the fact that plastic center relaxation is coming from localized events. Okay, where this average property like change in viscosity or average number of contact doesn't matter much. Whereas the slow relaxation time, it depends on system spanning events, so it will be sensitive to change in viscosity or average number of contacts. Because this fast relaxation time, it is more sensitive to local environment. Okay. So, Pawan, how much time?
You have 14.
Oh, okay. Okay, so now one thing is like I mentioned that for this dense suspension, the steady state behavior is sort of well known. So we tried to see, like we got different type of relaxation, like I showed that there is two-step relaxation, and for small step height or small peak stress values, there is continuous relaxation which is given by stressed exponential multiplied with a power law. So now what we'd like to do is like what is the steady state shear jamming prediction for this system? So what we do, we write the suspension viscosity is a standard form for jammed system. This is called Kraiger-Doherty equation. So it is telling that if your volume fraction is very high, approaching phi j, so eventually you get a diverging viscosity as the system solidifies basically. So now what we do, we just write viscosity like sigma divided by gamma dot, and we get an expression from gamma dot, and then we consider the non-trivial solution for gamma dot is equal to 0, that is given by jamming. One trivial solution is sigma is equal to 0, because if you don't do anything to the system, nothing will happen. But non-trivial solution will give phi is equal to phi j, and using again Watt-Katz model, that is given by this fraction of frictional contact, this f of sigma for a given stress sigma. So we can get a relation between stress sigma and the volume fraction, beyond which the system will jam, and all these parameters we estimated from experiments from steady state flow curves. So this is the shear jamming boundary. That means so for very high volume fraction you have isotropic jamming. What does it mean? That means your volume fraction is so high that the system is solid anyway, you have put so much particle. This region is not accessible for experiment. Now this shear jamming, it is telling that you can, at low stress you can start from a liquid like state, but if you increase the stress it will enter a solid like state that we are interested in, and this is the boundary. So it is telling that if you are below 56% you can never hit the shear jamming transition. Now on the steady state shear jamming diagram, we just superpose the nature of relaxation that we reported, because we didn't expect any connection between these two, but looks like something is there, in the sense like inside this shear jamming boundary, this green region, we get that the form I showed you, this power law cut off by stressed or compressed exponential. So that is this green region. Now if you go to higher value of stress, in the red region you get two-step relaxation, and you see plastic center in this region, because in green region if your stress is not so high, you don't see any plastic center. Okay. And interestingly, below this shear jamming boundary, we found that you can feed the data fairly well just with a stressed exponential function. The functional form completely changes. Okay, so this is interesting. We don't know like what is the basis of this difference yet. So last thing I wanted to tell you is see, for wide range of volume fraction, we found that this top boundary beyond which two-step relaxation comes and plasticity comes, this is fairly flat. And the stress scale is given, like in our case we got this 16 kilopascal approximately, except for the fact that for very, for lower value of phi, but still inside the shear, so there is some deviation. But apart from that, like in these region it is fairly flat, and you get 16 kilopascal. Interestingly, this 16 kilopascal you can get from the ratio of this PG as surface tension, which is 50 millinewton per meter, and particle diameter in our case is 2.6 micron. The ratio of these two gives you this stress value. So now looks like there is some connection with the confining stress, which is not unreasonable, because you can imagine that what is plastic center, how we see it. So what we found is like these bright spots are like excess protrusion actually. In these region the particles protrude out more, so they scatter more light and so on. So now you imagine you have some very less modulation of the interface. So this side you have suspension, the other side you have air. So imagine you have very less modulation, but near a plastic center, since the particle protrudes out significantly, you have a very, very sharp curvature, which is the radius of curvature is of the order of A, the particle size, then this stress you get like at least this much stress you have inside your system. That's why the particle is pushed out so much. Whereas remember the steady state case I showed you, they found that the stress, the peak stress is given by this 0.1 time gamma over A. Because in steady state you expect that much less modulation of the interface. Why? Because if you have plasticity, that is one advantage of transient measurement. If you develop plasticity and if you keep on shearing, eventually immediately your system will fracture. So that high stress scale is not possible to access using steady state rheology, only transient rheology you can. So this is something new, we are still thinking about it, but we used smaller size particle and we found that indeed this peak stress scale goes up. So we are probably on the right path, but more work needs to be done. So now I'd like to conclude. So we showed that there are two distinct transient stress relaxation regime in shear jam dense suspensions. Okay, using in situ boundary imaging, we showed that this localized plasticity gives rise to fast relaxation, whereas system spanning dilation results in slow relaxation in the system. And we have also indirectly confirmed such mechanism by changing the solvent viscosity and so on. And there is some interesting correlation between transient relaxation and the steady state shear jamming flow curve. So we'd like to understand better that why there is a correlation with this boundary that is predicted from steady state rheology basically. And so I didn't show anything, but if anyone is interested, I can discuss. We are finding, we are finishing up the experiment, very interesting memory effect in the system, because the idea is like memories are like we study memory effect in glassy systems and all, because out of equilibrium system they typically show memories, because equilibrium state, it doesn't have any memory of how the equilibrium is reached. However, this system we found that okay, so you apply some force and then it relaxes, the stress is completely relaxed as the system goes back to liquid-like state. And we'd like to think that liquid-like state will not have any memory. Whatever you did, it is erased because it has reached some liquid-like state. But apparently it is not. Like if you load the system again and again, it can show some interesting trend, which is very non-intuitive, I would say. And we also confirmed this by imaging and so on. So now these are the future directions. So now one question is like, what is the nature of this plasticity? In our case, we define plasticity like I told you, that this is the bright spots that is eventually like leading to fractures. So we are like kind of concluding backward that maybe these individual ones are localized plasticity. This is not a formal way to define plasticity. Plasticity in glasses and all, you have to calculate the mean squared displacement and larger mean squared displacement. But unfortunately, we cannot see the particle for longer time. Probably one can index match and do some confocal imaging to get better understanding. But now we did some experiments which might reveal something interesting. Is like so suppose this is the force chain structure for the shear jam state, which is like there are so many contacts, the particles are constant. It gives rise to a solid-like state. So now, actually, we think that this plasticity is coming due to the buckling of this force chain. Why is that? Because of this experiment, what we did is the following. Now, these are high-speed imaging because the relaxation process is fairly fast. So you have to go to 500 or 1000 frames per second to probe this. So what we did, we apply a step like I showed you, and you get these bright spots which are here, you can see barely. There are only few bright spots. Now what happens if you apply a second step in the same direction? So what we found is if you apply second step in the same direction, this number of bright spots increase actually. And interestingly, the older bright spots still remain. That's why we think that it is a buckling phenomena. It is not like that you are creating new plastic centers in the expense of older one, or older ones are going away. And this is highly directional. Now this I told you that I am applying first step and we are going in the same direction, and you are creating more plasticity. What happens after first step you create plasticity, and if you go back, okay, so that is the second case. You see like you have a lot of plasticity after first step. Now if we go back, immediately you see that if you go in the other direction, the plasticity is gone. So this is highly directional. So, and another important point we need to address, that is a more like long-term thing, is the connection between the relaxation of shear jam system with other dense disordered systems like glassy systems and all, where we also get strongly non-exponential and two-step relaxation. All these things are there, but for glasses it happens typically over much larger time scale. Often the relaxation is not complete, whereas for shear jam system it is happening over a time scale of second. So although both are like dense and disordered system, and they show some overall similarity in terms of non-exponential relaxation, but why this difference in time scale coming, that is very surprising to us. So all the experiments are done by my grad student Satchidanand, and we thank Yatindran for SEM imaging to characterize the particle, and these are my current lab members. And for funding, I'd like to thank RRI and SERB. And if you are interested, so this paper came a few months back, you can take a look. And thanks for your attention.
Thank you, Sayantan. We have about 6 minutes for discussion, so please feel free to ask me questions. Yeah.
Actually, you can hear me. So actually, in the case of like excess trace study, which you have done for distinguish between the localized particle for the short time and system spanning for the long time, one comment kind of I was thinking like it could be due to the additive effect which you were kind of remarking in the last, because the time you have done is like initially you have taken some time, the delta t is same, but longer time for the same delta t you are getting more thing. Like I was thinking like it is kind of additive for the throughout the time, and because it is the time origin is not same.
Yeah.
So that's why I was thinking it is kind of.
That's a good point, but that is not really true, because you have to remember that the x-axis is log scale. So, sorry, if I.
Means it might not be exactly additive, but it is kind of.
No. I know what you are meaning, but just a second.
Go back to the display.
Okay. I think
display maybe.
Yeah. Display we have to duplicate. Yeah. Okay. No. So that's a important point. Let me just spend a minute on this. Yeah. You are right that time origin is not same, right? So see here, what is the time here? It is roughly 0.2 second. And for example, I take this longest relaxation, so which is 2 seconds. So 2 minus 0.2 is very large. Whereas this first step, it is happening, the total time is less than 0.1 second actually. 2 minus 0.2 versus 0.1.
Yeah, but you showed image mapping, right? You go a couple of images back, maybe. There was a comparison between like a short time back.
Yes. Here also it is the same. See here, because you are confused because this axis is log scale. So here if I take the difference from, let's say, here to here, so this is again 1 or 2 seconds minus 0.1 second, which is negligible. It is like 1.9 second or 0.9 second, versus this first step, it is like happening over everything is happening over 0.1 second. You are correct if this is a linear scale.
No, I understand. I'm not saying it is just additive linearly, not linearly. I'm saying it is coupling altogether, because when it is
coupling,
localized
yes,
for a short time and you are checking again 100 means forgot the time scale.
Yeah.
But it is then as a total it is system spanning, because the time origin is not following up, like because the delta t was same but the phenomena was different. For the short initial time when you are checking, it is localized, so it could be like it is coupling all together, and at the larger time it is
no,
it's not like
so see
this one.
Yeah, this one. So see here we have taken some relaxation during the first relaxation process. So you can take, actually you can shift this time origin. So for example, I can take shorter time. It is not that it will be less. It is not like integrated, because after the step actually this picks up suddenly. It is not a like gradually it increases.
But the delta t is same, right? So the time
delta t is
matters here. So that's what I'm saying. When you are tying
no, what matters is the initial time. What is
initial time? Yeah.
Initial time.
That's what I meant.
That is the whole point actually, because this is whether you are in dilation relaxation regime or plastic center relaxation.
It was also coupled to the last point you make, maybe the transient state and the steady state. So when you are starting the process, it will directly affect that which state you are in, to get that you might miss the localized part.
Yes. So that is your second point is a good one, because see, that is steady state is more very close to that slow relaxation process.
Right. Yeah.
The fast, because that is the definition of steady state, right? Like you look at time scale where all the initial things have settled down and system. So typically that is much slower time scale. So that slow time scale becomes correlated with those processes. That is true. Yes.
Thanks.
There might be time for only very short question, maybe.
So I mean, I don't know if you explained like what was the reason, I didn't understand, between why the normal stress increases at when the I mean, I don't know if you explained that.
Yes. So actually, like, see, you have, I don't know that board. So you have a dense system, like you have all these particles. Now, when you shear it, actually you have different velocity as you go down, right? Because that is the velocity gradient. Now that means like next layer is going faster than this layer, because that's why you are having gradient. Now to go like that, the next layer particle has to move over the bottom layer particle, because they are not like point particle, they are finite size, so they have to climb up and like jump like this. So under that condition, there is a like overall swelling of the pack, because otherwise if they are static, you can actually put them maybe in a very nice order, like you don't need to put like on top of each other. But when they cross one another, at some point they have to climb up the particles basically.
So does this depend on hardness? For example, if you emulsion, then you probably won't have this.
Yes, no. Because you don't have, that is a good point, because if you have softer particle, if they can deform, this effect will not be there.
Yeah, we'll take one final question and then.
Briefly, right at the end you said if you reverse the strain, your plasticity also goes away.
Yes.
So in what sense is that plasticity rather than something that's non-linear elastic? Because plasticity normally by definition is not reversible. So can you clarify what you mean?
Yes, so that is based on the observation, because see, yeah, that's a very interesting point, and honestly we don't understand, because see, the plasticity we are defining by the fact that if you have some isolated bright spot and you load the system in particular direction, you first see that there is accumulation of plasticity along lines. And that line actually, if you keep on shearing, it creates fracture. So now, so if you have accumulated plasticity that is created by deformation, shearing in certain direction, now we found that if you reverse it, those bright spots goes away, and same as like, for example, I'll give you an example that you apply 50% strain. Now suppose you go to 50% more in one direction, you create a crack. But now you you shear 50% first and then you apply 50% in the reverse direction. You will never create a crack basically. So in that sense, we are thinking it is an observation, but you are right that plasticity, by definition, it is the irreversible thing. So we don't understand what event can give rise to this.
Yeah, in the interest of time, we'll conclude the talk and thank Sandra, a very nice, interesting talk. So now we switch over from jamming to active buds, and the next speaker is Shraddha Mishra from IIT BHU, and she will be speaking on active passive systems and some interesting dynamics.
Thank you, Pawan. I'm audible at the back? Okay, and thank you, Pinakida and Arnav, for this invitation and giving me opportunity. And I really apologize before starting my talk. This is the first time I'm presenting this topic. I have been presenting especially the slightly different from it, but again active. So if there are some missing points, you are free to ask questions and fill it up with time. So title is slightly different from as in this given to before, but the content is same. So I'm going to present basically how the active medium is going to induce some kind of effective forces between the passive particles. And in general, if you place some particle in some medium, there are forces, but I'm really going to quantify those and see what is happening. But before going to my talk, I would like to acknowledge the people who has contributed here for this presentation today. So this work is mainly done by my previous students, two of my previous students, Sudipta Patnaik and the Jayaprakash Singh. And actually the motivation for overall this topic started a few years back with the late Professor Aditi Sima and her student Pritha Dolai. And there are other students who are working also in the active matter, and financial support from the DST SERP. Okay, so this is a very brief outline of my talk. So I'll give an introduction to, because this is the first talk in this, at least for this session, on the active systems. I have to give that introduction to these active particles, or maybe the self-propelled microswimmers, which are also called the active Brownian particles. And then if these particles are in collection, then they have a very interesting phenomena which is called the motility-induced phase separation, and I explain during my talk. But today's topic is basically if I have a mixture of active and passive particle. I am not going to give a very much detail of when only the active particles are in suspension. And then how we are modeling this, how we are modeling this mixture, and then our results, conclusions, and future directions. So this slide is taken from a review article, and actually even this, basically all this data is obtained from various different studies. I'm sorry I could not put all those references here. I just put this review article here. And there's a very nice review article for understanding the dynamic and steady state properties of active suspension and various different passive particles in active suspension. So this x-axis shows basically a variation of sizes of particle of these microswimmers, which varies from, you can see, from fraction of micrometers to some of the order of few centimeters. And this y-axis represent their typical speed. So their speed varies again from some micron per second to maybe some fraction of millimeter per second. And there are various different examples of particle. There are natural as well as man-made or lab-made objects. There are just few points about these particles. So they are self-propelled and Brownian particle. They are self-propelled because each particle has some kind of asymmetry in their body itself that gives them the direction of asymmetry in which they propel. There is no external direction, or there is no external drive which is guiding them to move in that direction. And they can be natural as well as they can be designed in the lab, and there are many other talks also in this meeting discussing that. Sorry. And as I already said, they are microscopic and nanoscopic in size, have a typical speed of fraction of millimeter per second. And the interesting thing about is that they constantly take energy. If you don't feed them, then they are dead, and all this interesting thing will go away. They constantly take energy from their surroundings and convert it into the directed motion because of their self-propelled nature. And they have an asymmetry which gives them the direction. And in the artificial, these microswimmers, there are typically 4 types of, there can be other types, but typically there are 4 types of artificial microswimmers. The one can called as the Janus rod, which are basically the rod type. They have some kind of a shape asymmetry, but they know which direction to move. There is a difference from forward to backward. Then we can have perfectly spherical objects like a Janus sphere. They know forward to backward, but shape-wise they are symmetric. They can be also chiral. There can be some kind of a helicity in their rotation, and also the vesicles. And these are few examples. So this slide just shows the variety of systems of a varying length scale and the velocities in this system. Now suppose before going to the collection of such particles, what happens if we have a single such particle, and we can call it the single active Brownian particle. Active because they are self-propelled, and if there is a activity is off, then they are Brownian particle only. So this is just a cartoon of this particle. It has some kind of long axis along this body, and there is a velocity in that direction, self-propelled velocity in that direction. And since it has a long axis, or maybe the direction of this velocity can make some angle with some reference direction that I will call as phi. And this is sufficient to design this particle for modeling purposes or to understand this particle. And this velocity of this particle is actually make it, or the self-propelled velocity of this particle make it active. If one tunes this velocity of this particle and just draw the trajectory of this particle for 4 different realizations starting with the same point. So these are the typical trajectories for 4 different velocities varying from 0 to 1 micron per second, 2 micron and 3 micron per second. So we can see for the 0 or the passive case, it's a very confined trajectory for all 4 different realizations. But as one increases this velocity of the particle, the trajectory extends. But at the end, it's all diffusive. If you calculate some quantities like mean square displacement and all, at the end everything is diffusive. Only for the larger velocity it shows the extended trajectory. If one do that measurement and look at the mean square displacement of this single particle, so one can start writing down the equation of motion for the dynamics of particle. And in general, the example I have given, those particles are in the suspension, which one can actually forget about the inertia, and one can model it about using the overdamped dynamics, such that I can directly write down the x dot and y dot in 2 dimension. And then the first term here is the self-propulsion velocity times this orientation I have already mentioned, and this is a thermal noise. There is also thermal component into it for the position x and y, and this is simply the rotation, which is again had some thermal noise or the thermal rotation present with the rotational diffusion dr. So one can solve this equation, or one can actually find from using this equation, one can calculate the mean square displacement, which can be obtained like this, and tau r here is simply the inverse of this dr, 1 by dr. And then one can see that the mean square displacement for the late time, when the time or the tau is much larger than this rotational time scale, times here, then it's at the end it's a diffusive. But in between, it actually shows this kind of a curve. This is a mean square displacement plotted for different cell propulsion speed, which is coming here in the second term here. So for the zero cell propulsion, it's actually diffusive from very early to the late time. This slope is 1. But once we increase this v, it shows the initial growth of v square, t square, and then it goes to the linear. It's a kind of a super diffusive or the ballistic to the diffusive as we increase v, and this time scale from the ballistic to diffusion increases as we increase v. Using this expression, one can calculate the effective diffusivity, the effective in the system, and the effective temperature, and which is actually simply the actual temperature plus a piece, which is directly proportional to v square. And this calculation can be done very simply, just in few steps. It's very easy to do. So this is for the single particle. Now suppose we have such particles in collection. And then what happens? Suppose we have some particles in some system and they are interacting, and collection means they are interacting now with each other. And if we try to understand the collision mechanism between two particles, how the interaction is giving some interesting thing. So suppose two particles here, and they are like a genus particle which can distinguish from head to tail, and they are spheres such that they don't have any long axis in their shape. They cannot align in some sense, they cannot be like a parallel kind of a thing, but they distinguish from head to tail direction. So suppose the two particles are colliding head on, and since they have a self-propulsion speed, because of that they automatically get a kind of increment in the time with which they are moving in the one direction. Due to that, they will be forming after some time this two particle cluster. And now, because of their mechanism that there is a self-propulsion still in these, for this particle in this direction and this particle in this direction, before they actually can basically again break from this two particle cluster, it is possible that the other particle can also merge and they can form the three particle cluster. And this can happen at very low density. We don't need to go for very high density to find this thing. And this has been already observed in the experiments. So this is a typical snapshot of these particles at very low packing density of 0.1 or between 0.1 to 0.2. And we can see they form cluster, and different color shows actually the different clusters in the system. And also this is a typical picture to show how this clusters actually is stable. The tie size of this cluster is stable with time. So suppose there is this kind of a cluster is already formed. And this particle which is pointed in this direction, it moves from this cluster, but before that, at the same time, this another particle from this direction comes and join, and then this cluster more or less remains its site. So this is at low packing density, and these are the experimental system. But there are also study in simulation, and there are actually a lot of studies in simulation, which shows not only they form cluster, but they can also show the actual phase separation in the system, when the more or less all the particles in the one cluster. And in this simulation, interesting thing is that in the experiment there is always the thermal noise is present, the dt in the previous equation I showed is present, but the simulation can be also done with switching off the dt to just understand whether this mechanism can be seen without the thermal fluctuation present. So this picture, this is a simulation of many of such particles at different packing densities, and this picture on this picture on the left shows the for the same particle, these is like a soft spheres for when they are passive, and this is when they are active. They have a finite self-propulsion speed, and for two different packing densities, this is at low packing density 0.3 and this is at higher packing density at 0.6. We can see that in the purely equilibrium system, there are some clusters, because this color shows the density in some small region. So there are some clusters as we increase the packing density, but not like a macroscopic clusters are formed at this packing density. But in this active system, or when the activity or the cell propulsion speed is on, even at this low packing density there are small clusters, but at this packing density at 0.6 there is a one macroscopic cluster. So this phenomena of this formation of this macroscopic cluster is actually called the motility induced phase separation, because the motility of this particle, as I explained here, is leading to such macroscopic cluster at the end. Okay. Now, although this is not the key main topic of today's talk, but I want to explain that understanding the kinetic of this phase separation is also important. Today I am mainly going to focus on the steady state of this phase separation or phase separating system. But even the kinetic is also important, and there have been study on this also. So one can actually write down the kind of a field theoretic equations for also to understand this phase separation, and that is if we take the nomenclature from the equilibrium case where it's called the model B, then this is called as the active model B. There is activity present. And if one actually start with a homogeneous state and start simulating the system with time, then one can see there will be this yellow region actually show that there is high density patches. Then it grows with time, and this growing of this length scale has a typical, it depends on time, with a typical growth. This L goes as t to the power not 1/3 as in the passive case for the model B, but it's a deviation from 1/3. Few years back we also studied this active model B in detail, and try to see how in detail how this ordering kinetics is different from the model B. And this length as a function of time is for different activity parameter lambda, which is actually proportional to V. And then we can see for the passive model it's roughly 1/3 always, but as I'm tuning this lambda or the activity, it actually shows a crossover from this upper line is 1/3 and lower line is 1/4. It shows a crossover from 1/3 to 1/4. Ultimately at the end the asymptotic growth for this active model B is 1/4, and this crossover time is actually, we have shown that it's algebraically decay with the increasing the activity. If you have a larger activity, then the crossover time will be will come sooner. Okay. Now suppose this is all about when we have only this active particle, larger number, many of them. But what happens if we have a mixture, if we have an active particle and there are some passive particles suspended in, and we want to understand what is happening to this passive particle. So there are various different studies for doing that also. So this is one work long back, it's around 22 years back, the experimental study in which there is a bacterial solution and some polystyrene beads are suspended in it, and they are very few in numbers. The interaction between polystyrene can be neglected. Whatever the dynamic is happening, all due to the bacterial solution, and obviously there are thermal fluctuation present also. But the beads are much bigger in size, so we can actually neglect that part also. So now this is a snapshot of the picture, and this is a mean square displacement of the polystyrene bead for two different concentration of this bacterial solution. And we can see if it is a purely polystyrene bead doing the thermal motion, then we expect that it will show you a straight line just parallel this slopes with the slope 1. There will be only diffusive behavior. But in the presence of this bacterial suspension in the background, it shows again the extended dynamic with the initial superdiffusion to the late time diffusion. And it has also shown in this paper this the crossover time from this superdiffusion to diffusion is actually depends on the density of the underlying bacterial concentration. So remember in the previous plot of MSD I showed that purely for the active particle the same thing, but even if something is suspended into it, it also captures that information and it gives the similar feature. And that the time scale, actually the crossover time depends on the density of the suspension, or one can say if one can tune the activity of this bacteria, then one can show that it also depends on the activity of the suspension. Now, this is like how its dynamic goes on, the mean square displacement or effective diffusivity of this passive particle. But suppose I have only two passive particles, suppose these are two passive rods placed in this background of active particle, which are the run and tumble particle, which is slightly different from ABPs or active Brownian particle, but ultimately late time phenomena is same. So then if we have such a system and just try to understand the force between these two rods for their different separation, and by varying the density of this background run and tumble particle. So this is a typical snapshot at the different separation of these rods, and in this paper it is shown that actually the force between these two particles very much depends on what is the density of this run and tumble particle in the background. Also the similar thing, but not that there are two particles, we have many of these passive particles in this simulation plus experimental study. So these blue particles are passive, and this red and bright this capsule type of particle are active particle. They have slightly the elongated shape also. And in this system, if one calculate the kind of the radial distribution function of the two passive particles, then one can show if one turn on this activity of these long particles, then we see very different radial distribution function in comparison to if this background particle or the active particles are simply the passive particles. So from this picture, and there are also various other studies also. So from these studies, we can say that first of all that the emissivity of passive Brownian particle shows an enhanced diffusion in active medium. Active depletion force between two passive particles, it can show that there is a kind of I should not have used a depletion word here, I'll come in the next slide, but one can show that there is a kind of active depletion force between two passive particles in the presence of active Brownian particles, and force can be tuned by tuning the density and activity of these active Brownian particles. Okay, so now that these things actually have motivated us to study this in detail and actually measure whether there is something, there is actual this force or interaction can lead to the actual phase separation in the system or not. So we started modeling this mixture of active Brownian particle and the passive Brownian particles. Actually, it's not Brownian, it's a passive particle only. The active Brownian particles are only having some kind of a fluctuation or the noise present here. So this is a typical equation for modeling this. This Ri, the first Ri is basically for the active particles, which are shown by this arrows with these red circles. They have a direction in which they move with velocity v, which is the activity, and vi is a simply cos theta sin theta in 2 dimension. And they also interact by some soft repulsive force. We have taken this the spring force, but one can also take some other soft repulsor like WC and all. And there is no thermal noise present here to just see whether this effect is present even without the thermal fluctuation. And these active particles can reorient their direction with some random rotation, which is given by this eta I. And the passive particles can move only through the interaction. If there is no interaction among the particles, then there is no dynamic of the passive particles. So we need to have these active particles to move around them. If we turn off or if we start tuning this V and go to very small v, the relaxation of the system will be very slow. We have not added any thermal noise to here, just to see that whether this dynamic of only due to the activity of this active particle can lead to the interesting thing. But in the experiment, there is always thermal fluctuation present. So now this is a cartoon of my system, and this force is also soft repulsion. So there is an interaction between active-active, passive-active, and passive-passive, all 4 types of interaction, and they are all of the soft repulsive interaction. So if one calculate the radial distribution function of passive particles, because we are interested in passive particles only, and I start varying the density of active particles in the background, so then we see this is a typical snapshot of my system. Remember, I kept the density of passive particles same in this system. And we can see that for the very small density of active particle, these are the gray circles here, and the green are my passive particles. And this is for one size ratio. This is a size ratio 10. It means the size of passive particles is 10 times the size of active particles. So we see this, there is not much interaction between passive particle and radial distribution function just show the few peaks at the start, but after that it goes to the homogeneous value. But now if I start increasing my density of active particles, then at some density it starts to show the very first peak, and after that there is a one broad peak which resembles that there is some clustering is happening among the passive particles, which is also shown in this picture, and this x-axis is rescaled by the size of the active particles. And that is why we see the first peak is coming roughly at 20, because the size ratio is 10 here. And now at the packing fraction roughly close to 0.5, all of these passive particles are at one place, and this we can call as like a full phase separation, and that is also seen in this radial distribution function of this passive particles. Now, what is the effect of varying the size ratio? There the size was fixed. So this picture shows if we start varying the size ratio. So this is for the small size ratio. Here the passive particles is approximately 4 times the active particles, and then I am going downward and increasing the size. This is as size ratio 10. So when we have a small size differences, then again there is not much interaction. There are first few peaks, and after that it decays to the uniform value. But as I'm increasing the size ratio, at this larger size ratio there is a more interaction, and again size ratio 10 we see the full phase separation among the particles, among the passive particles. So now we can, based on this observation, we have drawn the phase diagram. In the plane of the packing fraction of passive particle, although I have shown the picture for the active particle, but in the plane of this passive particle and the size ratio, which is actually more important, size ratio is more important for us here. And we have not varied the V, as I said before. If I vary V to very small value, then the system relaxation is very slow. Yeah.
Sorry, so around the cluster are the entities depleted, because I see this big kind of that region, yes.
No, actually it's just maybe a little bit wrong way of making picture. They are just at the surface. Yeah, it's not like this. Yeah. If you calculate the radial distribution of passive active, you will see the first peak at the radius of the active particle. Yeah. Okay, so we have typically seen the 3 phases. One is for the low size ratio, and for almost for all packing density we have seen there is a almost homogeneous structure, something like this. For moderate size ratio, there is this kind of intermediate clustering, and for this higher size ratio, this red triangles, we see that there is a full phase separation in the system. So now we try to understand what is leading to this full phase separation in the system. This study just showed that there is a full phase separation. We wanted to understand the force between these two passive, not two only, force between two passive particles in the presence of this medium. And since it is look like this force is more effective when the size ratio is high, so if we go back and look at the literature from the colloidal system, then there also we know if we have an asymmetric mixture of colloids, and if the size ratio is large enough, is large between them, then if the two bigger particles are in the contact with each other, or if they are nearby, such that there is a overlap of their excluded volume region, that actually lead to the more volume for the other solvent or the smaller particles to move, and that effectively lead to an kind of effective attraction between these two bigger particles, and this is called the depletion induced attraction, or this is also called given by the Asakura Osawa, and it's called the AO model also. There's a very simple, very basic phenomena I studied long back, and there are various different studies on this. But this range of depletion induced interaction or depletion induced attraction is actually just a few size of a few active, or not active, but the size of few solvent particles. It's not very big compared to the size of this whole system and the passive particle. We try to actually start understanding this mechanism in the similar fashion, but before that there is also one experimental study and simulation as well, where actually in this group they have actually tried to measure the force between two passive particles in the medium of this cyan and red particles, which are the active particles, and they showed that this force between these two passive particles is actually very much depend on the details of the system. They actually say that it's a constraint dependent active depletion force on passive particle. So we started measuring this force, and we actually modeled this in the computer. So we started with having two passive particles at a separation r, and there are background active particles, which are this this red particles in the background, and they are active. They have a direction which I have not shown here, and this is a one snapshot part of the system to show that there is a clustering around this passive particle. And then we started these passive particles at very close to each other, almost touching each other, and then we slowly make them, let them go away from each other. And the dynamic of this active particle is given by as before. There is a self-propulsion in the direction of their heading, which is a cos theta, sin theta, this Ni, and there is a soft propulsion among passive, active, and all four kind of interaction. And these active particles have some reorientation with this noise, which is eta I. And the passive particle is not undergoing any dynamics in our simulation, because we actually want them to be at the fixed separation so that this R is not changing, that they are frozen to their point. So we actually start with some separation, let the system relax, calculate the force between these two particles, these two blue particles at that separation, and then let again move it to slightly away from each other and redo the thing. And using this, we calculated the force between these two passive particles as a function of separation, and then we integrated it to calculate the effective potential between these two passive particles for different parameters. And key parameters here we varied is the activity of active particles. And now I can vary the activity because I'm not doing the dynamic of passive particle. The activity of active particles and the size ratio of size difference between these two particles. So this first picture here in the picture panel A shows the for fixed activity, which is in some unit, is in the dimensionless activity, is 160, and for different size ratio from this black to blue, it's from 4, 5, 8, and 9. And we can see for smaller size ratio for this activity, it's like for a very small distance, and this distance is again normalized or the rescale by the size of the active particle here. So for very small size ratio, it's like there's some small repulsion at the start, but then it's actually zero, so one can call it like a non-interacting. But as I'm increasing the size ratio, this interaction is actually becoming attractive. There is having a big dip here. And if you see, the range of this interaction is much larger than this size of this active particle. It's much larger than the depletion-induced attraction. And then in the second panel, we fixed the size to 10 and varied this activity from 40, 80, 120, and 160. And then for this bigger size ratio and for the small activity, although at large distances it's again zero, but we can see there is a difference from this black to black, the bottom black, that it has a kind of a repulsion, but it's a long range repulsion. It's not just like this kind of a short range repulsion here. And the zero means they are touching to each other. It's a surface distance. And then as I'm increasing the activity, it's again becoming attractive, and it has a large long range attractive interaction between the particles. So now after getting this potential, we wanted to understand whether this interaction potential is sufficient to do something to the purely passive particle. So we come to the second part of the same study. So now we have only passive particles, and we have feeded these potentials, the different parameter potential. We have roughly 100 parameters in our phase space. And we feeded this potential to this passive particle, which is actually given in this gradient of V effective obtained previously. And this V effective is a function of size ratio and activity and thermal noise, because it's actually a overdamped dynamic. We want some dynamic in the system. And we started seeing what is happening to this passive particle. Suppose I start with a very homogeneous kind of a system, and we have a very low density of this particle. They are packing density of 0.1 only, 0.1 to 0.2. And for different size ratio and activity, this is again the repetition of the same picture to show this as a form of the potential. So for all this range of different potentials, what we found, if we start with a homogeneous of this almost homogeneous passive particles, we find at the end we have typically 4 different configuration of passive particles. The one is where we see at the end also they are more or less homogeneous. If we calculate the radial distribution function between these two particles, it's almost like a one peak, and then it decays to the homogeneous value. For the second case, where we see some structures, but if we zoom in these ones and try to calculate some kind of a correlation or some hexagonal ordering, there is no such ordering. Although there is some density clustering, but there is no hexagonal ordering. That we call as a disordered cluster. There are clusters, but they are more or less disordered. And the third one, which is very interesting, we found that there are clusters and also perfect hexagonal cluster, which is actually, there are different spikes here. And the fourth one where we see there is a, not like they are coming close to each other, but there are obviously there are some structure in the system, and there are different kind of peaks in this system. So this phase we call as the order cluster, and this last one we call as the polycrystalline, because look like there are different kind of peaks in the system. Yeah. No, we are not changing the density.
The last one is the same density.
So all are at the same density. I don't remember, but it's between 0.1 to 0.2. All are at the same density. It's very low density.
So in the last case, is some sort of filling the space without.
But they are at a different separation. We have not seen the last one, what will happen if we increase the density. We wanted to, but in this study we have not.
No, but let's say when you supply this effective potential, so that the depth or the minimum of the potential sets up the scale, right, basically.
Yeah.
And then
The last one is not obtained for this potential. I'll explain for which one is obtained for which one.
The last one is a different thing.
No, last one is actually for this black curve, which has a short range repulsion, long range repulsion.
Yeah. Okay.
I'll come to that.
Yeah.
I'll come to that. Yeah. Thank you. Okay. So now, whatever we take, whatever this SNV we take, and by feeding all this potential, we always found only these 4 phases. We have checked, and basically for this kind of this first black here, we find the disordered one. And for these one, like this one, this brown color here, which has some attraction but not as deep as these ones, we find this kind of a disorder cluster structure. These order cluster are basically we have where the large depth in the potential, and this polycrystalline phase which we are calling is actually where we don't have any attraction but there is a long range repulsion in the system. So we have 4 different, we are not calling it phase because we have not characterized in that manner, but 4 different structures in the sample finally. So now this is the shows that if I feed these potentials, then we get the 4 different structures in the system. So now we try to characterize in detail or other details of these structures. So if we calculate the cluster size distribution of these clusters, and using this cluster size distribution, I can actually calculate the average size of the cluster, this M here. And if I plot it as a function of size ratio on the x-axis for different activity here, by increasing from black to this blue, I'm increasing the activity. So we see that for this average cluster size is actually is very much depends on the activity, and which we have seen in the previous plots also there are clusters and where they very much depends on the activity. And for each of these activity there is like a cutoff, or there is a kind of a critical size after which we see that there's enhancement in the average cluster size, and if you plot that the critical S as a function of activity, then it's actually decay by increasing the activity, which we can see from here also. So this is about the density cluster. But suppose I start to measure the structural ordering of there is a HCP structure or not for the different curves. So then this is a plot of size 6 order parameter, hexagonal order parameter, as a function of size ratio, and that we see that doesn't show very interesting, not very much dependence on the different activity, and that is almost flat. There is it's almost increases for the all activities. The critical S is almost same for different activity, and this table actually shows the typical numbers of these 2 parameters, the average cluster size and size 6 for 4 phases. So this error bar is actually for a different range of S and V varied, where we find these 4 phases. So for disorder cluster, this number is very small. I don't know whether it is visible or not, but I'll read. It actually goes from the average cluster size is just 8 to 12, and the size 6 is very small, 0.05. Then for the disorder cluster, we find it's roughly of order of 75 to 80. And the size is again small, 0.3 to 0.4. For the order cluster, we see the cluster size is much bigger, of the order of 200, and the size 6 is also large. It's of the order of 0.7 to 0.8. Yeah. And for polycrystalline, we see the cluster size, and here we have actually changed the distance criteria for measuring the cluster size because they form some structures. This is from 140 for the M, and for size 6 is of the order of 0.63 or so. So we have found the 4 different structures, disorder one which is for the small size ratio and small activities, disorder cluster for large activity and moderate size ratios, polycrystalline for small activities and large size ratios, and order cluster for large size ratios and large activities. And this is again to remind the 4 structures I've shown before. So now we first calculated the potential, and then we feed it that potential to the passive particle, and then we try to see what it leads to. But now suppose I take this active passive full mixture and feed the values of S and V for where we got the different potential, and try to see whether we can get the different structures of the passive particle in the system. So this is a full microscopic simulation of active and passive, and S and V taken from the same value as for different potential for the 4 different phases. And this is for the first case where we found a disordered structure, which looks more or less disorder as we have found before. I only focus on the red particle. The gray is the active particles. This is not exactly, but it looked like a disorder cluster kind of thing. There is some clustering, but not any periodicity. There is no HCP structure or very weak HCP structure. This is the order cluster, this one, where we see that there is a macroscopic phase separation, and also there is a perfect HCP structure. And this is a phase which is not exactly like a polycrystalline, but it looked like these passive particles are frozen to their position. And if we actually calculate the dynamic of this particle, they are actually frozen to their space. They are not as mobile as in the other phases. So this is from the full microscopic simulation, and with this I will now conclude. We have found that the passive particle experience an effective attraction in active medium. The range of attractive interaction is much larger than the depletion-induced attraction in asymmetric colloidal mixture. The nature of interaction and form of potential very much depends on the properties of active medium. The mixture can be replaced by an effective potential generated by the active medium, by our second part, and we found the 4 structures for the different parameters. And these 4 structures can be found in the full microscopic simulation of binary mixture. There are also some future work we are looking forward. First of all, this is for one type of active particle. So what is the nature of this effective interaction? Suppose I change the nature of active particles. Suppose I induce small attraction between the particles, or maybe they are slightly elongated. What is the dynamic of these passive particles in these 4 structures? And also, since they are phase separating for the order cluster and for some other phases, so what is the kinetics of that ordering, whether it is a kind of a passive model or there is something else. And we still looking for whether these structures can be called as a different phases, as there is a phase transition from one structure to other, or there is a from one phase to the other. And with this, I would like to thank you and take questions.
Yeah, so we have at least 7 minutes for.
Okay, thank you.
You take all the questions.
The first question is that so in terms of the potential that you computed, so if you in terms of the colloid diameter, how much it is? Is it because in terms of the active particle is around 20, 30 something.
I'll come to that because everything is scaled. It's easy to see.
No,
this is the active particle, and the size ratio, by using size ratio like this blue one, which is for size ratio 10, we can see, and this is actually the size of this dip. This 10 is roughly a one equivalent particle. Yeah.
Okay. So the second question, if I may ask, is that in the one of the 4 structures out of that, so you have one structure which is crystalline, but it has arms.
Branches, yeah.
Branches. So you have some understanding of
this
why the branches form?
Yeah, this might be because our potential has this kind of attraction. If it is in this range only, we have not plotted here, but it is actually 0 after it. If it is in this range, only they can feel the attraction. Otherwise, they are not.
Let's say, typically, if you have in a passive scenario, if you have this kind of much less density but lower temperature, then you are going to form a crystal which will be more circular.
More circular.
But because of the
I don't have a much understanding, but what I feel that now this one particle in this branch is non-interacting with this particle here. That might be one reason.
But is it evolving further or it remains like that?
It evolves, but more or less this branch is very stable. This branch is very stable. This branch is very stable.
We'll go anti-clockwise direction. We'll come back.
Hi. So how is it different from like a depletion interaction kind of stuff? Like if mixture of 2 passive particles and there is a size difference between them, they will also form cluster, right? So how activity is playing part? So suppose like if the size ratio is same in the active and the passive mixture, will they form cluster?
No, they will not. That is your more or less this one where the size are comparable. They are not forming cluster. The potential is almost non-interacting. The size ratio
So size
matters.
ratio, like,
size
should be
ratio
there.
matters, and activity also matters.
So kind of activities enhancing this depletion
Enhancing
kind
it,
of.
yeah, enhancing it, yeah.
Thanks.
So Rajesh and then Madan will come. Yeah.
A very nice talk.
Thank you.
So, a couple of questions. The first thing is, have you tried looking at the concentration dependence of your active particles, keeping the size ratio fixed? Does it have like a trivial dependence that you see with conventional depletion interactions?
We have, but not systematically, but increasing activity enhances this.
Yeah. So if you calculate the depth of the potential, does it scale with concentration?
That in that manner we have not, but we
Okay.
are looking forward for that.
Right. And the second thing is this length scale over which you get this attraction getting scaled up. Is there like an intuitive picture that you have as to why this happens?
We don't know, but first of all, you can also see, our potential is not very smooth. Suppose we want to do any fitting, and this data actually takes a lot of time to generate.
No, I agree with you, but it is clearly much longer range than. Right? So if you were to think of some length scale that comes due to the fact that you have activity.
Actually, I feel is a length scale is one major length scale, as the Smarjit was saying, is the size ratio of these two particles. So one can get some kind of, not exact scaling, but there can be some kind of dependence on that size ratio of these two particles. But no, other than that, I don't know the answer right now. Yeah.
Yeah, Madan has a question.
Yeah. Thanks.
Yeah,
nice talk, Shraddha. But I thought you might want to compare it with some analytical work done by Kafri and Karda.
Actually, I was not able to understand that much. That is not, because this is the first time I was presenting.
Yeah.
I will keep it at next
So
time.
because they have calculated using a multiple expansion the effective force between two passive particles embedded in a sea of active particles, and then they show that crucially that it depends on the shape of these.
Okay. Yeah. Sure. Next time I'll.
Not surprising because the pressure.
No. I knew. I knew
against
that
it,
work. I knew. But yeah.
And the other thing is these passive clusters that you see. Do they sort of eventually break up, reform?
Yeah, they do. They do. They have some statistics. Finally whatever I showed is the macroscopic one in the last picture. It's not like they are always like this. They have dynamic. They form and break.
So that would be very interesting too, because normally in conventional phase segregation, big clusters is thermodynamically very expensive to break them up.
No, but these clusters break.
Ones do.
Actually, getting this completely phase separated is very different. If you have some 500 snapshot, only 10 to 15 will have some.
So it turns out that there's some similarity between this and the fluctuation dominated FDR or FDL. Fluctuation dominated long range order. Yeah.
So they like this structure out of like say 10% time only, or maybe less than 10% time they're like this. Otherwise they're
there was one more question. Yeah, please.
One small question. This is again regarding this effective interaction. So you talked about this long-range repulsion. So do you understand? Did you try to fit the form of it?
No, we have not tried to fit any of it.
Any of it?
Yeah, any of it. But one can try. But we have not tried.
Because earlier we tried to look at this thing in the passive scenario.
Okay.
And so there we had this one so in the context of hydrophobic collapse.
Okay.
So there we find this 1 by r to the power 4.
Okay, I'll check with that one. Yeah, I have not. Right now we are looking.
But I'm not sure means things can be drastically different here.
Okay, I don't know. I can check that. Yeah, I can check.
Thanks.
That.
Yeah, so I have a question. So if you now consider the thermal noise, what you're considering in your simulations, the DT, what you were mentioning. So if you systematically kind of change this, would you also see some ramification on the assembly and also the processes?
By
for example,
tuning DT, you are saying?
by tuning DT, because for example, why I'm asking this is if you induce this activity through a thermal kind of perturbation.
One can actually, one can do that.
Would you also observe this? Because I assume you are actually taking the activity more from the viewpoint of, let's say, a chemical, like a Janus particle under some particular
This, the aim of turning off it is just to see whether this phenomena is purely active or not. But we have also run the simulation with small thermal noise, and we do see this clustering. But I don't know what is the effect of varying it. I don't know what happens for very high. But obviously, if you have a very high, then activity is not very important. In that manner, some of things can go.
Okay, one more small question.
So I was thinking, is there a correlation between like the density of smaller, the active particles, and because I see like the crystalline cluster of bigger particle, it always happens at high density region of smaller particles.
High density of active, high activity of active, and bigger size ratio.
No, that is true, but I'm talking about the local picture, like where it is happening. So it is always inside the sea of.
That is a main. This is actually not only here. It's mostly if you have a one big passive and you just submerge into the active medium, you will find that the active particles are surrounded there. But this will, and since it is a cluster, then it is happening in a more strongly here.
Okay. So one more.
Please.
So as this in experiments, do you think this hydrodynamics is important?
That's what we are looking at in collaboration in Pune with Vijay, and some of his students are already here. In hydrodynamic, we don't see the full phase separation. We only see the small clusters. So we are trying to, not doing the actual hydrodynamic, but can we mimic the hydrodynamic by doing some other interaction force? But hydrodynamics will play some role.
Okay. Thanks.
Okay, we started with the box, then with the turbulence, then we went to the aspects related to the jamming, and then we are closing with the activity. So with this, we conclude the session.
Thanks to all the speakers for the very nice talks, and thanks to Pavan for an excellent chairing of the session. So, this is regarding posters. So we had sent you this email for the flash talks. Please send the slide to the person concerned so that we can organize the session properly. So it's at 3:15, if you remember. So please send the slide by 2 o'clock, make sure. Put your posters, there's enough space, so make sure your posters are up. And the other logistic thing, don't lose your badge or forget to wear your badge. This is your ticket for lunch, dinner, breakfast, everything. Okay? And for tomorrow's